All right. Good morning, everybody. You're watching a live camera feed from RV Falcor 2. I'd like to welcome you to dive 710 for ROV, remotely operated vehicle Sebastian. This morning we are here in a new location, which we are calling Blanco West 1. Basically, we've shifted over overnight, done some multi-beam mapping, and we're going to look at sediment routes south of the what's called the Rayas Delta and west of the Blanco Yelcho river systems. I'll put up a little map in a little bit for you all to see as we're transecting here. We've got a couple hundred meters of transiting here, so that's why you're seeing a lot of blue water. And while we're transiting, we're also operating the M3 sonar system on the sub. So that's a little intro into what we're doing, but you're going to get a lot more details here in just a second because I've got Dr. Sebastian Watt sitting here with me. Also in the room, I've got Claude and Andy as my pilots today to my left, and then behind me I've got marine technician Josh O'Brien, but we call him Josh.B. Josh B. Also in the room I've got many scientists from many disciplines joining us for this expedition, and you'll also be hearing from them in a little bit. As always, if you have any questions whatsoever about anything you're seeing on your screens, just pop it over into the chat on YouTube, Facebook, and Twitch. And with that intro, I think we're hearing a little vessel stop, so I think we might be arriving soon. I'll pass it over to Dr. Sebastian Watt, who will be telling you more about what we're doing today. All right.
Great, many thanks, Sophia, for that introduction, and thanks to everyone joining us today. We're on our 8th ROV dive of this expedition. So over the last week, we've done those 8 dives, and we've been moving southwards along the inner seas of southern Chile. So we started off a few days ago at a port called Puerto Montt. We spent a couple of days in a fjord a little way south of Puerto Montt called the Relancavi Fjord, and there we were looking for evidence of the impacts of volcanism on the sedimentary systems and marine environments of that fjord. And that was a sort of small study area that was aimed to help us compare and plan that main study area, which is what we're in now. So we've moved southwards from that first site, progressively through this the glaciated landscape of this continental shelf, which is marked by a complex series of channels and highs, and we're seeking to understand this environment in a general sense, but specifically the impacts of volcanic eruptions, large explosive volcanic eruptions, on this environment. And the particular event that is a major focus for this expedition is the Chaiten 2008 volcanic eruption. And we are right now around, I would estimate, around 20 kilometers west of Chaiten volcano, which is a sort of near coastal volcano in southern Chile. And Chaiten erupted in 2008, and it deposited large volumes of volcanic materials over the landscape. These were materials in the form of ash, so sort of sand-sized fragments, right through to large blocks of pumice. And these volumes of sediment were remobilized by rainfall in the days after the eruption and carried down into local river systems. And there was such a large quantity of material that this overwhelmed those river systems, really transformed their behavior. And as this slurry of volcanic material was carried down towards the shoreline, the sheer volume of material exceeded the capacity of the river channels. In the Blanco River, which comes down through a town also called Chaiten, a coastal port town, the Blanco River simply couldn't carry the volume of material that was inundating this river system, and a new channel was cut right through the town The banks of that river overflowed with this slurry of volcanic sediment, and this flooded through the town and very rapidly built a delta that projected for about a mile beyond the previous coastline. So in a matter of hours to days, this sediment was carried down into the delta system. So this transformed the coastal environment, had major impacts in the town of Chaiten, which had been completely evacuated by this point, so a very rapid evacuation after this eruption had started. But what has not been studied before is the impacts of this major influx of sediment, this major environmental disturbance in the marine environment. And that's really what we're seeking to understand here. The reason we want to do this is first, to understand the effects of a major disturbance on marine environments and ecosystems and how those systems respond and recover. We want to use this event to understand sediment pathways and transport and the interaction between sediment input and currents through these shallow seas. So these are not widely studied, well-known, well-mapped seas, so everything we're finding is new. And if we can understand the sort of fate of that material and how it accumulates on the seabed and where it accumulates, then potentially we also have a route to go back in time through older deposits from events that we might not even know about, to read the pages of that book of volcanic history. So if we can understand this event, it's sort of a key to unlocking deeper records of past events. If we can find areas where these deposits are accumulating on the seabed and where we can potentially sample them using what we call coring methods. So coring methods allow us to punch down into the seabed and recover the stratigraphy, the depositional layers that accumulate on the seabed. And this is, a very common principle and method in geology to read the past, to go back into the past by looking at those horizons of materials that record past geological events, past geological conditions and processes. So we're applying that same principle here, but to really interpret that stratigraphy, we need to understand how an event such as Chaiten is recorded, is sort of imprinted into the geological record. So these are the various sort of aims of our expedition. A lot of unknowns because this is not a well-studied region. So we're learning a lot as we go along. We're having to question our original sort of perspectives, I guess, of what we would have expected to find. So we're having to sort of adjust our hypotheses as we move along. As we get new data, new observations, we're getting a better understanding of the currents in this region, the depositional processes, and then we're planning our next sites in light of that. So this is a sort of, fast-moving and exciting way of doing marine geoscience, and we're finding new things on every dive. So as Sophia was just saying, on this dive we've come out a little bit south of our main target site, and we're aiming to transit across it, slightly above the seafloor, which is why you're not seeing the seabed at the moment. That transit will give us a short but very high resolution sort of strip of mapping data which we can later interpret to understand the structure that we are aiming to dive on. Now we've chosen that structure based on seabed geophysical data. That is both superficial mapping data of the properties of the seafloor, both the topography of the seafloor, so its shape and height, but also its backscatter properties, which essentially tells us about the nature of that material making up the seabed and how reflective it is. So we can tell between harder and softer materials. And what we've noticed in this region is that we have an area of higher backscatter than to the east, which is probably where we would like to aim to dive later. And in this area of high backscatter, we're seeing some unexpected features that we've been discussing in the last half day or so to think about what these may be and whether they might relate to the glacial history of the region, or perhaps whether they have other origins in marine processes that we will need to interpret. So alternatives could be that they are Some have tectonic related features, so related to faulting in this region, and this is a very seismically active region. But it is also a region that was covered by thick ice during the last glaciation. So if we were here about 20,000 years ago, we would be sat on an ice sheet several hundred meters in thickness that would have extended right out to the west to an island called the Isla Grande de Chiloé, which is probably the limits of that ice sheet would have been about 100 kilometers west of here or thereabouts. So that's what this environment would have been 20,000 years ago. And now it's covered in about 140 meters of seawater. So these features on the seabed are a little bit puzzling, and we're landing on actually a crossing point of two of these features. So they're essentially sort of streaks, broadly linear streaks with higher backscatter, with a range of orientations, but two principal orientations. We'd like to understand them, and we'd like to understand what is making up the seabed in this area, what we would call the substrate. So the sort of the rock type or the material type at the seafloor. So that's what we're seeking to understand on this dive. The mapping transect that we're about to take, as well as the video data, will be really informative to help us interpret that, and of course sampling as well. But in this case, actually, the imagery, I think, in the first instance, will tell us a lot to help us test our interpretations. And then we'll seek to collect some samples. Whether we can collect cores here will really depend on how hard or consolidated that substrate is. And that's a little bit of an unknown until we get down there. At the site a couple of days ago, our dive site a couple of days ago, the seabed was much coarser than we were expecting. It was rich in angular pebbles and cobbles, so pieces of rock, loose pieces of rock up to about 20-30 centimeters across. I think we saw many of them on the sort of 10 centimeter scale, and these were not rounded like typical pebbles you might find at the beach. These were angular, which suggests a possible relation to glacial processes. So we're sort of building on those observations and that interpretation. And this dive is due south, a few kilometers to the south. So we're sort of wondering whether we're going to see similar deposit types or materials on the seabed here. But we'll really have to see when we get down there, because at that first site a couple of days ago we did not see these linear features on the seabed. So this is a new thing in this area. Now the seafloor to the east of here, back towards Chaiten town, which is where we would like to go later, that has a very different feature in terms of its backscatter properties. So this sort of this reflectivity, if you like, that we were discussing earlier. That is lower backscatter, and we might infer from that finer sediment, less consolidated materials, and certainly in our geophysical data we see more extensive, continuous and slightly finer scale layering, material that we think we're more likely to be able to core. But as we've already found on these dive sites, it's hard to forecast exactly what we're going to be able to do until we get down there and get a good understanding of what's on the seabed. And this is, of course, the great benefit of being able to use these technologies that we're using here, this ROV, which is controlled by the pilots to my right, and we're able to explore the seabed with this in amazing detail, with the imagery, with the capacity to take samples, with the other sensors on the remotely operated vehicle. So this is really incredible to be able to, as geologists, as marine scientists, to be able to use this to gain a big advance in our understanding of this region. So we're really finding out information that we simply had no way of accessing before. So this is all new, it's all exciting. Who I've got in the room with me are various colleagues. So I've got Dr. Becky Totten from the University of Alabama.
Roll Tide.
Behind me. I allowed a pause, knowing that she would say that. So she can tell you a bit more about her interests. And then next to her we have Gianluca from the University of Valparaiso, Universidad de Valparaiso, working on the marine biology. So he is logging the things that we're seeing. I guess he's not logging much right now, but he's keeping a sharp eye out for things as they come in. And then we more to see on the seabed. And then we have Amalia and Mana from Universidad de Chile, and Mana will surely be going to University. Do I have to say it again?
Get ready.
I have to say it again. To the University of Alabama.
Roll time.
Jill, do you want to say anything on this?
What's that?
Do you want to say anything on this? Do you want to sort of introduce yourself? So I've also got Jill Pelto, who is an artist, and I'll let her introduce herself actually and talk a bit about her work and interest on this expedition.
I know this one's on. She's also a geologist, so art and geology
With a background in glaciology, is that right? So yeah, well suited to this project.
No, I'm so sorry. Can you do that later?
Right, thanks, Sophia. So we're back. Thanks everyone who's joining today. I can see there's quite a few questions and comments building up, which is great to see, and we can certainly be answering some of those questions as we go down to the seabed. So for those who just joined us, we are west of the town of Chaitén in southern Chile. We're about 10-20 kilometers or so from the town of Chaitén. We're pretty near the coastline, so when we look out of the windows on the ship at the moment, we can see forested slopes, so steep slopes, quite dramatic topography. It's cloudy here, but you can see hints of snow and ice on the caps of those peaks. And this is a landscape shaped by glaciation, still with ice caps on the high mountains and volcanoes. So there's a large glaciated volcano not too far from here, called Minchamahuida. And adjacent to Minchamahuida volcano is a smaller volcano called Chaitén, which was not a particularly well-known volcano at all until 2008, when it had a large explosive eruption which devastated the local landscape, caused major impacts in the town of Chaitén, which was completely evacuated. And we're not far offshore the town of Chaitén right now. And what we're exploring in this expedition is the impacts of that 2008 Chaitén eruption on the marine environment. Now, those impacts are a consequence of extreme sedimentation following that eruption. We know that sedimentation occurred because of observations we can make on land. This is actually what caused so much destruction in Chaitén town, in a process called lahars. And lahars are generated from a mixture of volcanic materials with water that forms a dense, fast-moving slurry. So like a flood carrying very large volumes of sediment, if you like. And this inundated Chaitén town. It overwhelmed the capacity of the river system. And when that river slowed down and reached the sea, that sediment was deposited. This built a very large delta in a very short amount of time, extending the coastline by about a mile offshore the town of Chaitén. And we expect that large volumes of sediment went into the adjacent ocean. And what has been studied at Chaitén a lot is those sort of terrestrial impacts, but there's been no study to date of those marine impacts. There's a number of reasons why we'd like to understand that. That links to one of the questions here, actually, is someone asking about the ecosystem recovery after these events, so that they cause, or we expect them to cause, burial in places, very rapid burial. And one thing we're really interested in is the consequences of these events, how far-reaching those consequences are in the marine environment, and how those systems recover. So that question is sort of hitting on exactly one of the questions we have as well.
That's a 20-meter overlap you have here.
We've gone beyond. Could we do slightly further? That's all right, please. Yeah. So just discussing with one of the ROV pilots aboard here, a transect that we're doing. We're essentially moving over our study sites to collect a short strip of mapping data, and that's because we're trying to examine a feature on the seabed that we think may be related to glacial processes and exposed on the seabed, or may be related to other processes shaping the region, perhaps tectonic processes and faulting. So we'd really like to understand what this feature is, partly to understand how we can interpret the seabed morphology and features in this region, and also if we can understand it, it gives us some insight into the age of particular stratigraphic layers, so particular layers on the seabed that will help us understand things like the rate at which sediment is accumulating. So that's our target on this dive. And on a later dive today, ideally we would like to move to the east, closer to the delta offshore Chaitén town, where we expect to see more evidence of the sediments directly from the Chaitén eruption, and perhaps earlier volcanic events as well. That's 50 in total. Yeah, I think that's good. No, I think that should be good in terms of the in terms of the features we're on. So if we could turn back towards the waypoint, please. As I was saying earlier, for those who were on, there are a lot of uncertainties when you're studying a new region like this. You're drawing on existing data sets, which in this area are relatively limited, low resolution. So all this new sort of higher resolution data we're obtaining is all new, and it's all telling us new pieces of information which we're interpreting as we're going along. So we've been having a lot of discussion as a team about what these observations are that we're making, how we can interpret what we've seen on the ROV dives or in the samples that we've collected, and that is then shaping our decision making for the next sites. So a lot of rapid decision making and discussion as these exciting results are coming in, and we're learning all the time more about the marine processes shaping this environment in the modern day through currents and the sort of modern oceanographic conditions, the interaction with the local river systems, including those around Chai-10 volcano, which were transporting all this volcanic material, and past processes, including those linked to glaciation of this area, the tectonics of the region, and of course volcanism as well. So a complex interplay of geological processes that we're seeking to explore. So as I said earlier, we've got various other colleagues here in the room, and I was about to introduce Jill Pelto, who is an artist from the US who is joining our expedition, and it's really exciting to have her with us. And she is going to talk a little bit about her interests and what she's doing.
Yeah, I think so. It's awesome to be able to talk during the dive, and I'll share a little bit about what I'm doing here as the artist at sea on this expedition. So I have a background in climate science, specifically glacial geology, and so it's cool to have the connection here and kind of filling out more of my understanding of ocean science and working with such a diverse group of scientists in terms of volcanologists and sedimentologists, marine biologists, and more. And so as the artist, I'm coming in and getting to learn a lot of pieces about this research, and my role is to make art, and for me that's paintings about what we are finding. And so as an artist who is making work about science and trying to communicate that better to people, I kind of think about breaking it down in terms of a story, and so showing how the data is collected. Like right now we're doing this ROV dive, we're taking sediment samples, taking cores, looking at the features on the seafloor for mapping, and so I can interpret that in my artwork. I can show the visuals of how we're collecting this data. After kind of showing how we're doing it, I want to try to paint what we're finding, and so we're finding landforms. What are we finding in the sediment, like finding tephra from the lahars from volcanic activity, and so once I can kind of show what we're finding and show that story, one of my ultimate goals in probably like a final painting is to show why that's important and kind of understanding this landscape, how dynamic it is, and why that's so important for local populations to understand the past and present history here. And so it's been a fun challenge where the science is ongoing, and so I'm trying to make art as it's happening, but a lot of the most exciting stuff just keeps getting more exciting. We keep learning more, and so a lot of what I'm able to capture is stuff as it's happening, versus a lot of times when I make art about science, it's going to be after the fact and we have our results, and I can show that really clearly. So it's been a fun challenge to think about how do I show things as it happens, as we're learning before we know all the answers. And so so far I've made a painting about all of the different devices that we're lowering from the ship, from the Falkor 2, and
it's beautiful.
Thank you. And just showing that visually, showing the types of devices that we're lowering. And my next paintings I want to show some of the cores that are being collected, so I can highlight what we're finding in them in terms of the sediments and how that varies based on the landforms, based on where we are relative to Chai-Ten volcano. And so I'll show the cores, show what we're finding. My other two main ideas are, one, to show some of the mapping that we're doing, because that's going to really highlight better the bigger scale landforms. And we're doing mapping of the bathymetry of the seafloor, but then also sub-bottom profiles where you can get at that sediment layer. So I want to show both of those in one piece, that aerial view and then that profile view. And maybe highlight a few really cool structures in the profile. So maybe something like the deltas that we're seeing, for example, and glacial features that we're seeing, but kind of that profile side view of what those structures look like. And kind of for a bigger final painting about the project, it's something I would probably start on board the ship and complete later, but I want to show a bigger landscape that really speaks to a lot of the story of what we're doing here. So showing Chai-Ten volcano, showing Chai-Ten town, maybe some of the surrounding islands that also have populations, but then going all the way down to the ocean, showing the boat in the image, showing the seafloor in the image, so kind of going land to sea. And I've been speaking with the teacher from Chai-Ten area, Danny, who is on board, about what to kind of include in that overarching painting, because it's going to be showing the science, it's going to be showing the landscape, but an important part of the story is the culture of this area as well. And it's rare that I can include that perspective from someone who can speak to that and can tell me what might be good to include about what the community thinks about this research, what they think about what we're learning about their landscape, kind of how closely their culture is tied to the landscape. So that's kind of the final piece that I want to make, and my plan is to share all of this artwork with the science community on board, with the communities local, which Danny will help me with, like sharing some of the art with some of the schools in the area that she teaches at, and sharing it at an exhibition that I'm planning in the United States in this spring. And that exhibition is all about glaciers and their contributions to ecosystems. And so this story plays into that with this glaciated volcanic landscape that is really dynamic and affects a lot of people who live downstream or near these areas.
Could we just wait a couple of minutes for it to settle? It's interesting. It's really
So I'm getting to observe right now all the researchers in the room kind of making decisions about what they want for sampling locations, and so they're looking for areas where they can take cores. And sometimes, or often, you have to go and just try taking a core. Sometimes the sediment is difficult to core through if it's really firm.
I think we'll see how the first two go in. Sorry, after the consistency. We'll see how the first two go in, and then we'll potentially get two more. But then we will also provide more and then potentially a trend sector. Just to try to get to see if we can change the seafloor across this feature. So I think we've been on a couple of minutes already. So can we find these please?
One more.
Yeah, just two, please. This is on seafloor. Number two. Number three. Right, so I think we'll try push cores here, Becky.
Definitely.
Yep.
We want
Right.
push cores.
Push cores, yes.
The biologists are like very excited after the last couple of sites where they didn't have much biology. This mud should have a lot of critters in it. So fill up as many as we can.
It's there's not a lot immediately visible though, Becky, right? Compared to some of those seabeds we saw with all those echinoids. And things,
Yeah, but
a
if
couple of days
you
ago.
look at the surface there, yeah, maybe there's not as many benthic organisms just sitting on the seafloor, but I have a feeling there's quite a bit of infauna because it looks like there's Gianluca, PhD student from Universidad de Valparaiso, is giving me the thumbs up. There's little sort of dots or pockmarks there you can kind of see.
Is that going into
Those are
that?
actually little holes where maybe worms are living or other organisms that live inside the sediment, the infauna as we call it. And of course, our colleagues here in Chile are looking at polychaete worms and nematodes. So if those are worms, this is a really, really great site for the marine biology team. Okay, everybody cross your fingers, toes, arms, everything that sediment stays in. Oh gosh, you didn't cross them hard enough, guys.
Very loose.
Okay.
Okay.
So we had a
Maybe
bit
we
of a
could try
chat.
another one, just going a bit deeper to sort of
You want me to bury it?
bury it, yeah, just to see if that helps.
Sometimes if we
That's
push the
discovery.
cores in really deeply, then it compacts that clay so that it becomes a little bit more cohesive and stays in the barrel. Yeah, and you can see where it fell out, that little area where it plopped out there on the seafloor from this push core that we just took, that it is a little bit more cohesive, it's sticking together. So if we can do that a little bit more, push it in a little bit more, it might work better. Might stay in there.
You want all the tube clear?
If we can, as clear as we can, please, thanks, yeah. It's looking pretty clear now, isn't it? You're in something hard there. That's interesting. Yeah, okay.
Yep. If you can push into that hard.
I lifted some up.
It lifts it, yeah.
Oh.
The ROV, so it's hard.
Wow. Okay.
Okay.
Does that make sense with geophysical profiles that we have of the seabed?
It may do. At least I think we got better recovery though here. So
Crossing my fingers. Just a little bit longer.
excellent.
Make it in there. I think.
Yeah, at least it's looking good. Right, so just for the log, the push core was, after that full depth, hitting something very hard, but too hard to push into anyway. I think we'll try to finish the dive with a bit of a transect, or at least in the later part of the dive, do a bit of a transect to see if we can get a sense of variability in the seafloor, because we're in this sort of high backscatter strip, but the edge of that may look rather different.
You see the arm clock?
Okay. So challenging operation, as you can see with this ROV. This is very skilled to be manoeuvring these and getting these cores back into their holders. And with such soft sediment, pretty tricky to ensure this all stays in there. So that's great. We've got the first one recovered. And the reason we're collecting duplicates of these is because we like them for different purposes. So we can use them to look at the biology of what's in there. We can use them to look for changes in the chemistry of these materials, and we can use them for chronology as well, to also try to get age information on these. So Becky, I don't know if you want to talk a little bit more about what we would use these push cores for, and why we've got sort of multiple samples of the same
We
material.
wanted more push cores.
I
Yes,
could talk
please.
all day about what we're going to be doing on these push cores, but I'll limit myself. I'll control myself. So we're going to talk, or what we're going to do here in a minute is we're going to talk about how we're going to sample these cores when they come up. So there's a few different things that we're interested in here, but first and foremost is we're looking for volcanic deposits here, and we want to know what timing of each one of these volcanic deposits are, so that we can link them to things like the 2008 Chai-10 eruption, or other past eruptions of that volcano or other volcanoes in the area, like the Yate, for example. And so one of the most important things we can do on board is look for samples to date. And the material that we date is usually carbonate. That's the best material to date here. And so we're looking for things like shells. They're the same composition as Tums that you might chew on if you have a bit of a stomach ache, if you've eaten something too acidic. And so we're looking for these carbonate shells that we can then send through a mass spectrometer and look at the ratio of different radioisotopes of carbon, and actually then determine the age of the sediment that those shells are sitting within. So ideally we will look within these cores when they come on board, and either find things like clam shells within that sediment, or we'll sieve out the mud, so wash the mud away and look at the coarser fraction, at the sand size particles within these cores, and sample tiny little shells called foraminifera, which are these single-celled organisms that live both in the water column and on the seafloor, and they make some of them make their houses out of calcium carbonate. So we can date those and have a really good idea of the timing of these eruptions. One of the most important things too is to look at what's living within these environments today. So we have our colleagues from Universidad de Valparaiso here, led by Eulogio Soto's team. Diego and John are here sitting behind me, logging all the marine life that they see. But when these come up on board, they'll be sieving, washing the mud away themselves, and looking for all the soft-bodied critters in here, namely worms. But my team, including Mane Heberlein and Jacob Helgeson from the University of Alabama,
Roll Tide.
will be looking for the forams, looking for these single-celled organisms that are much smaller but can tell us a lot about environment, since they're very sensitive to changing water conditions. And if we stain these living organisms today, we have this thing called rose bengal that we use to stain living tissue. We can actually radiocarbon date the living organisms and have an idea of the reservoir here locally to calibrate the record. Thank you. Awesome job, guys. It's a good push core. So we'll be looking at a lot of different things. We also will be looking at another tiny organism that mainly lives within the water column, but can also live on the seafloor, where you have light penetration. So probably not in this region do you have them living on the seafloor, but they certainly live within the water column and then settle down. And those are phytoplankton called diatoms. And so we've already seen these clay-rich sediments throughout our cruise. Any place where we're finding clay, we're finding diatoms, and Mane always gets very excited, comes running and says, you know, oh, look what I found in the microscope. There's a lot of that happening on board right now. And so we'll look at the diatoms that settled from the water column to learn more about the past conditions, especially following volcanic eruption events. So ideally, where we find something like an ash layer in these sediment cores, we'll look just below the ash layer, try to get a date with those shells that I was talking about, but also look at the diatoms to get baseline conditions. And then we'll look above the ash layer, maybe try to get another date so we can really constrain it both above and below. And then also look at the diatoms and forams that tell us about water conditions, nutrient conditions. There are certain diatoms that bloom under high nutrient conditions, and certainly a volcanic eruption. Woo, push core 3. Awesome job, guys. We're just getting better and better at this. We have very experienced ROV pilots operating today.
Fourth one?
Yeah, let's take a fourth one because I think that'll keep the biologists back here very happy. We'll have, okay, we're asking for a total of 5 push cores now. Yeah, so we'll have a few different things we can do on these cores. We'll archive one just so we have a record of all the stratigraphy, meaning the layering in the core. So completely undisturbed. We'll just take a subsample of this core with a smaller tube and tape it up and take it back to our university. And then the other cores will actually extrude like a push pop. So we take that top part off of the core tube when it comes back up on deck, and we set the bottom of the core tube onto, I mean, it really just looks like a push pop. Any kids of the 90s here will know what I'm talking about. So you just set it onto another cylinder that's slightly smaller that fits just right inside that isotopes of carbon and nitrogen throughout these cores to tell us about how the environment's changed, how nutrient conditions may have changed, especially before and after eruptions, like I was saying a moment ago. We'll look at the tiny shells, the diatoms, the foraminifera, and then the biologists are, you know, sediment layer to have a really good understanding of what's living there today and how healthy this ecosystem is. I don't know how aware everyone on the audience is, but certainly was news to me. You think of these areas as being, you know, pristine and untouched. It's got this beautiful rainforest here in southern Chile, but actually there's quite a bit of pollution and contaminants that make their way into these systems, and things like polychaete worms tell us a lot about the health of the overall ecosystem.
In the science team, wide range of nationalities and institutions represented, a wide range of disciplinary backgrounds, and we're all working together and bringing our own sort of insights and expertise and interests in this project. And it's quite rare to be able to work on a scientific project with such a large and diverse group. So that makes this and marine science in general very exciting. So we've got a lot of Chilean scientists here on the project. And as I think Jill mentioned, we've also got a school teacher from Chile, from the region, and she has been working a lot on our outreach activities, including the ship-to-shore sessions. We've had a lot of those. In fact, we got one this morning, I think, with local school groups. So that's really great. This is quite a remote region of southern Chile. Chaitén. So I was in Chaitén actually shortly before the eruption, and this is sort of really coincidence. But when I was doing my PhD, the field area that I was studying as a fully terrestrial volcanologist, so I hadn't even thought about any marine science at that point. 1,000 years. Had an interest in that region ever since. And actually was fortunate enough to work in a field team in the aftermath of that eruption as well. Particularly mapping out the tephra fall deposits. So these are the ash deposits that go up into the atmosphere and then fall out essentially a sediment settling through the atmosphere, fall out onto the landscape below. And this ash blanketed right across Argentina, blanketed the landscape, covered a huge area. I'm trying to think how to best give you that area. I specified it to someone the other day in units of the size of Wales, but I don't know how many people on the chat will understand the size of Wales. But the area in Argentina that we mapped was about 8 times the size of Wales, which had some coating of ash. Now, in many areas that was very fine. That was sort of sub-millimeter scale. But a huge area of Patagonia was received direct ashfall from this event. Now, when you have an eruption of this type, some of you may be familiar with events like the Mount St. Helens eruption, for example. When this ash is deposited, it gets thicker and coarser towards the volcano. So it may be that can be carried down by rainfall into these river systems. So I'm just going to have to discuss with Andy the plan for the next part of the dive. We've got 5 push cores, right? Now, Becky, what's your thought with fibre coring? It's hard beneath, but I think...
Because we can get a good water sample.
Sorry, just having some discussion here. Becky, I think...
We need to do a 6 because the 5 was very bad.
Let's do a 6
But
push core. If that's
I'm just wary about later in the dive, we want to do a bit of a transect about keeping one for something we might find, just so we have some capacity.
Okay, so maybe 5 will be for biology.
Because we have been using some disrupted ones for biology because they can use a bulk.
Are you cool with that?
So-
You can have 5.
The 5 push core here,
Yeah.
it's bad, so it's 4.
But that's okay, they'll use it for biology.
You mean it's bad in the sense it's disrupted?
Yes.
That's okay for a bulk sample. Yeah. So I think we just have capacity that way.
Yeah.
So Becky, the decision is whether to try a vibracore. The seafloor's hard. I think it may struggle, but I think it's worth still trying one. And see.
Yeah, if we can punch into whatever that
Yeah,
hard
exactly,
layer is and at
exactly.
least get a
So
little
I think it's
like
worth trying one.
sample of it.
But probably not trying 2 if it fails.
Yeah.
Or at least doing transect
Yeah,
first.
so then we have capability
So we
to
have
do both.
capabilities. We only
Okay.
got 2 with us. Yeah.
Okay.
Yeah. So
Do
can
we need a scoop though as well?
Yes. Shall we? Should we do a scoop first? Because that may give some insight into what's underneath.
Yeah, let's do a scoop first.
Okay, can we do a scoop back, please, Andy? So, as you might have heard there, we're sort of having a discussion over the next best steps, and this isn't always clear. We have our initial set of objectives, which is that we'd like to, well, essentially recover as much as we can to achieve all the science aims. But the reality is, when you land, of those materials may not be quite what you were expecting. It might not be possible to use all these methods. We're just discussing there whether the vibracore is likely to be successful in this. We were getting a sense from the push coring, those tubes we were just pushing into the seabed, that there's a hard surface beneath this veneer of muddy sediment. Those push cores are 30 centimetres long, so about 30 centimetres down there seems to be a hard layer. Now, we'd like to know what that is. In our geophysical profiles, this is a layered substrate on a sort of 10, we can visualize about 10, 20, 30 meters or so, and it's layered, perhaps on a sort of meter scale. So there's several horizons in there, but we can't really tell from that how consolidated this is and whether it's going to be possible to core it. So the push coring is suggesting this is quite hard, but we are going to see if we are able to at least penetrate some way into it with the vibracorer. But we decided to take a scoop bag first. So these are principally for the biologists to get a bulk sample of the surface sediment. But taking that scoop might potentially reveal to us, just with the cameras, some more information about that underlying hard surface.
Yeah.
So we shall see. Perhaps we can sort of dig away slightly at this upper surface.
I think we're right in it though.
So being too deep,
Rodrigo was supposed to pick me up from the printer, the new ones, but he didn't.
So if we can get the scoop, that's handy. Yeah. Okay. Let's see what we see. Yeah. Suspect we won't get any visibility.
Could you get me these off the printer? There should be like 3 copies.
So, Gianluca, I don't know if you want to say a little bit about the types of organisms that you're interested in. So in Spanish is absolutely fine. You know, so as I was saying earlier, we've got a lot of Chilean scientists here. We're communicating in both English and Spanish, and I think we've likely got some Spanish speakers on the feed as well. So Gianluca will just be describing some of his interests in Spanish.
Buenos días a todos. Bueno, me presento, soy estudiante de Biología Marina de la Universidad del Paraíso, ya de quinto año, actualmente realizando mi tesis de pregrado en el último semestre. Bueno, lo que nosotros estamos haciendo acá, estamos tomando 4 réplicas diferentes, ya quiere decir que en el mismo sector donde se tomó, se acaban de tomar los pushcore para la... 4 réplicas, que en este caso serían esta bolsita, del mismo sector, para poder estudiar la macrofauna bentónica que vive en el sector. Bueno, podemos observar que sobre el sedimento no se encuentra fauna visible al ojo humano, ya, y es por eso que nosotros llevamos estos saquitos a un tamiz, a 3 tamices. Ya primero pasa por un tamiz de 1 centímetro, luego pasa por un tamiz de 500 micras y finalizamos con un tamiz de 300 micras, donde principalmente y mayoritariamente estamos encontrando poliquetos, que son gusanos submarinos, ya de la misma, del mismo tipo de lo que conocemos como las lombrices, los gusanos de tierra. También estamos encontrando hartos moluscos, hartos caracoles, un par de erizos por ahí en algunas estaciones, ver bajo microscopio.
They're close, so maybe we don't want to try that one. We try a more obvious one.
We want to go. So we want to go across this.
Cut across it.
So what about north and then?
What if we kind of go over
Okay.
and up
Yeah, we could
here,
do a square.
and then over here,
Yeah.
so we can see
That's a good idea.
this
Go over both.
linear feature and then that one.
All right. So we want to go west, north.
Yes, west, north, east.
Okay.
We're doing the Roomba. The Roomba. Thank you.
Right, Gianluca. I was going to suggest we move about a bit to see local variation rather than
Oh yeah,
collecting.
but how many?
We've got 2 scoops here.
from here. Yeah.
So the problem is if we collect 4
Yeah,
here, you won't
Yeah,
you won't
it
be able to get more later.
Yeah,
in the
but
day.
it couldn't be that far away from the push course. That's the.
So you would rather collect 4 here,
Yeah.
even though we might not
Yeah.
have capacity.
Yeah,
Okay.
it's okay.
Okay.
So if we could get 2 more, please. Ross, thanks. Andy,
But
sorry.
it can be more in this area. That would be good.
So where we punch for the push course, that's where we want to scoop that whole area.
Okay.
We want them to be really
Even though it's
associated.
it's the same materials, yeah. Nane? Hey Karen, that's awesome that you're teaching your students about marine sediments. We love talking about marine sediments here. Good morning. Hello to all your students. Where are y'all joining from? Students watching and learning about this very underexplored area of southern Chile. We're in northern Patagonia here, and just to give you guys an idea of how exploratory this is, most of the maps that we're making, we've never seen the seafloor here before at this resolution. We have navigation maps that are really coarse resolution, not much detail. And as we are mapping the seafloor, it's almost like, going to the moon in a way. Going to the seafloor is like going to the moon, in that we're able to see a lot of features that we haven't been able to see before at high detail. And of course, one of our big challenges here on board is, as we see these features, a lot of them are surprises. So we have some geological
problem solving to do today. We have some puzzles that we're hoping to solve, or at least partially solve. And one of the things that we were most excited about here is that we have this finer grain sediment. So where we were looking just over the last couple of days, we were really excited that we were able to test based upon the geophysics. We thought this might be an area with more mud, and look, here it is. We're sampling the mud.
Thank you.
There's lots of surprises everywhere we go because it's so underexplored here. So if exploration sounds cool to you guys listening from afar, I hope that this kind of inspires you to know that there's so much about our own planet that we really don't know, and so much left to explore. We know a lot more about the surface of the moon than we do about the bottom of the ocean. So what we're doing here is just adding a lot of new detail to our understanding of Earth processes, especially near these volcanic centers in southern Chile. Right, Seb?
That's right. We're learning more all the time. Yes, and there's lots still to learn. I mean, one of the interesting things, colleagues on here from Senejemin, the Chilean Geological Survey, and they were talking about their work in monitoring and risk and managing volcanic hazards in Chile. It was a really interesting discussion we had afterwards. But Calbuco is high on the list in terms of the sort of monitoring efforts and the frequently in its past history. So the last 200 years, Calbuco has had a lot of eruptions. Most recently in 2015, but also large eruptions in the 1960s, others in the 1900s, and through into the 1800s. So it's quite an active system. And yet, when we go back earlier into the geological record, so into what we'd call the Holocene record, so around 10,000 years, slightly longer, 10,000 years or so back in time, the eruptions from Calbuco that we can reconstruct, that are preserved, or that we know about, preserved in soil profiles or lake sediments, there are far, far fewer. So it's our picture of Calbuco's activity is that suggesting an event every couple of thousand years. Now known historical observations which show a highly active volcano erupting every few decades perhaps, and a geological record that suggests a much lower eruption frequency. And this is very typical of our ability to reconstruct long-term volcanic histories. And this occurs because it's really only the biggest events that have the best potential for long-term preservation in the geological record. So when we reconstruct these volcanic histories, we tend to find evidence of the big eruptions, and evidence of the small eruptions disappears. It's very hard to find evidence of. We can learn a lot from the evidence of those big eruptions, but it's not a complete picture, and it's not it's not the ideal picture for reconstructing a full understanding of a volcano's behavior. If we're only seeing the rarer but bigger events, we might also be interested in those smaller events and understanding how often they occur. Smaller eruptions can still have very significant consequences. And actually that does sort of link to the aims of this project, in that we're trying to find new ways of reconstructing volcanic records with different types of materials. That's really part of our interest here in coming into marine sediments adjacent to these volcanoes and seeing if there's different ways in which we can access evidence of past events and their consequences. So that's exciting, it's new, and whether that's a technique that we could extend is really a question that we want to address from this expedition, and it's a bit of an unknown question at the moment. So until we can really understand what we've recovered here, where preservation may be good, where preservation may be poor, we can't really understand the potential for developing those sort of longer term, newer volcanic histories. So certainly one of the things we want to do, if we can understand the Chai-10 deposits, how it's dispersed, where the products of that eruption are ultimately deposited in the marine environment, if we can get that understanding, then we have a good prospect for then targeting deeper events and maybe looking at unknown eruptions from Chaiten or Minchimahuida or other volcanoes in the region. So lots that we hope to be learning through this expedition, through our subsequent work. So we'll be recovering these samples, they'll be coming off the ship, and then we'll be working together as a team. Teams from the Universidad de Chile, from other universities in Chile. We've just been hearing from Gianluca at the Universidad de Valparaiso. We have colleagues here from other universities in Chile. Becky from Alabama.
Roll Tide.
Yeah. I couldn't really avoid saying it there. Could
Yeah,
I? But,
yeah, it's gonna.
We've got people from Malta, University of Malta. So from New Zealand, we've got Javier from Auckland, Anka
yeah.
from Massey University.
Yeah.
And from the UK, we've got myself from the University of Birmingham with Keris, PhD students, and Alistair from the University of Edinburgh. So, and I've
Woohoo.
possibly, I hope I haven't missed out. Oh, we got Matilda, of course.
We have
from,
Matilda.
from OGS in Trieste in
yep.
Italy.
Yeah,
And
she's-
she's heading up our geophysics team.
Yeah, she's a very good leader. She's a magician with, all of our geophysical data. I'm seeing in the chat the class that joined is from Houston Community College. Big shout out to y'all. I went to Rice and worked in Houston for a little bit. I love Houston. It's great. Kind of miss it sometimes, but I also love Tuscaloosa. All right, now we're talking about what we want to do with the scoop bags. Is that like a cucumber? Or it's a worm, you think? Kind of
So
fat.
we're zooming in on this this interesting looking worm,
Wow.
which we can see here in the scoop.
Wow.
This is way beyond my area of expertise.
Okay, and so-
experience.
so-
Maybe Gianluca can.
Well, maybe we should say Gianluca is entering our event log, trying to take note of everything we see. So one of the things that Seb said when we first got here is, wow, I don't see as much life. There's not as much sitting on the seafloor in the way of, clams or corals or things like that. But then I said, oh, but look at all of these little holes in the seafloor. Those are little access points for all of the worms below. So I think this is one of them. There's lots in the seafloor here. The in fauna seems to be pretty abundant. And the oxygen conditions here are 86%, so pretty high. We're at 134 meters water depth. So not too deep. Oh, whoa. I'm just hoping it doesn't come out of that bag. It'd be cool to get it. Oh. Okay, this is like slow motion. No. Is it in there?
Yeah.
It feels like we're playing with a balloon, trying to keep the balloon up. I think it fell out.
You can suction it, right?
Could we get it with the next scoop?
I think, isn't that the fourth scoop?
That's a forest.
That was the full scoop.
We have one more.
We have one more. No, we
Do
have
you want to get
more.
one more scoop just for this guy?
Yeah.
We can.
Was that the third we collected, Claude, or that was the fourth?
I think I can see it. Look.
You have a spare one. Okay.
What do you think it is?
If there was a way of just getting it, that would be great. Thank you.
Akura. Organism is that, Diego?
It's on an
Scoop?
yeah.
Oh, it's an annelid worm. Okay, cool.
No, two.
And you can see like where the opening is when we were looking at it. It kind of comes to a point, almost like the end of a sausage.
Yeah, like a
It looks like
sausage.
a sausage. Some boudin up in here, making me hungry.
Maybe it can, because for the size it can be very large.
For the what?
Maybe seeing
Is that
the
the sort of
size.
thing that you're interested in?
Maybe it can be size and
So,
Oh yeah. So Diego's saying the size of this organism also helps in identifying species.
be.
Yeah, I think we can see it on the camera. We'll be able to get it. We'll just have to be extra careful. Yeah,
Oh, really?
I think that's it.
Thank you.
So this is pretty deep in the sediment, wouldn't you say? This is, you know, more than 5 centimeters into the sediment below the surface.
Yes, yes.
So that's a great example of in fauna. It's living in the sediment, not on the seafloor. If it's on the seafloor, we call it epifauna, for on top of. Somebody called this a sea sausage. Yes.
Yeah.
I know. This is making me hungry. I guess we're getting close to lunchtime.
It's not making me hungry.
Clearly, you're not from Louisiana.
It's only half 10.
Okay. All right.
Oh, someone on the chat saying that maybe people do eat these worms.
Oh. All right. Well, I don't think we'll be able to try it on this particular expedition. I don't think that. I think that is frowned upon for us to eat our specimens. And actually, I don't know if you guys know this. Let me talk a little bit more about what crazy things geologists do when we are characterizing sediment and describing it, which we do a lot of. We've got our student Alistair here from postdoc. Whoops, Dr. Alistair.
My young face.
Yeah, from University of Birmingham and
Edinburgh.
Edinburgh.
Was it Birmingham?
Edinburgh. So he was a student at Birmingham, and now he's a postdoc at Edinburgh. And I'm saying that correctly.
You are.
Yes.
Not
Okay.
Edinburgh.
Yes.
That's wrong.
Okay. Scots are very picky about these pronunciations. Anyway, so when we bring these on board, Allie's been doing a lot of work in describing the cores, describing the sediments that we see within them. And one of the things that we do typically to see if there are medium-sized particles in there, silt-sized particles, because they're kind of gritty. They're not clay. They're larger than clay, but they're not quite as big as sand, is we actually munch on them to see if there's grit in there. So geologists tend to eat rocks. We either are licking the rocks or we're chewing on the rocks. And here we all had to tell our geology students and postdocs not to eat the rocks because this particular area could have quite a bit of contamination. So we're using other methods of, settling it in a small glass dish to see instead of munching on it. Allie, do you want to say any more about that?
Can do, yeah.
I'm going to just give you the reins here.
Go through the process of eating worms.
Cool. Yeah, so I'm a postdoc at the University of Edinburgh, and I'll talk a little bit about the process that we do when we recover these cores and these samples. So, particularly in the vibrocores, for example, we'll take the liners back up, and we'll remove them and keep them upright, so there's no sediment or anything is disturbed, and then we start to cut down and cut the top of the liner off. And as we start to cut down, we push down and extract as much water as possible, so we can see where the sediment surface is. And this is quite a long process to try and get as close to the sediment but without disturbing the sediment. And when we realise that we're close to that, we cut some foam and we put this in the top of the barrel, and we essentially seal that and cap it. And we do this for the bottom has got the core catcher in anyway, so this keeps it nice and tidy. And then we keep this in a freezer so that all of the material is preserved. And then when we're ready to split this, we take a blade and we take a saw and we cut the top and the bottom, and we cut this very, very carefully down the edges of the barrel, and then we split the core in half. So sometimes this
requires us to put a few spatulas in and to prise the core apart. And once we've done that, if all's gone well, we have a nice intact stratigraphy or layers of these sediments and rock types. And we take this into the lab and we clean this up. So we use sort of round edges spatulas, glass slides with rounded edges to clean these very carefully to make sure that we don't contaminate any of the layers with other layers in the core. And then once we've done that, we end up with a set of, hopefully very nice layers that are preserved there. And then a description process begins. So we work through this. This we normally describe from the base to the top. However, we measure everything in cores from the top to the bottom. So we'll measure our gap at the top where the foam is, and then we'll start from our sediment boundary. And from that we start to measure the group things together in terms of packages of sediment. So this is looking for really subtle changes sometimes in terms of changes from silt size material down to clay, which is really difficult to tell. As Becky was saying, we often put this in between our teeth as geologists to see if it's gritty or not, as this is really microscopic. So yeah, you need a microscope to kind of measure these things. With our eyes, with a hand lens or magnifying glass, it's really difficult to tell between these different sediment types. In this case, we're not doing that. We're taking some toothpicks and we label up where we want to take our samples from. We put them into the sediment and we take a tiny amount of sediment within that, and we disperse this using a dispersant or using water. We sometimes use a potato as well as a starch in the potato, allows the grains to break apart and not stick together as it dries.
The British style, isn't it?
So we just put our toothpick with sediment on top of the water or the dispersant on the slide, and this spreads out the sediment across that. And we dry off the water, and then when the water's all dry, we're left with some sediment.
Frank? Did you tell him about Frank?
Wait, what?
We have a potato mascot in the lab right now.
Yeah, I was just talking about the potato. So the potato's called Frank, and he's got some googly eyes on as well, and yeah, he's getting smaller day by day. Yeah. So it's a bit more crinkly as well, but we keep him in the fridge, so it's nice to have him. And so when we've got this sediment that's dispersed across the slide, we dry off the water, and then once that's all dry, we add on a curing agent. So in this case, we put on a glue which cures in UV light. So we put a few drops of that and a cover slip on top, and we get this to cure under UV. And once that's all ready, we can look under a microscope and we can look for the grains that we have.
Cheers. Thank you.
So if there's a particular layer which is light in colour or dark in colour, it depends on the composition of tephras and things like that. We've got an ash layer that potentially might be within the core. We can look for volcanic glass. So when volcanoes erupt, they erupt juvenile material, which is a fresh magma that is driving that eruption. But they also erupt crystals, and they also erupt what we call lithic or accidental clasts, which are parts of the volcano or the deeper structure of the volcano that the energy is blasting through these rocks and also including them in the material. So so we can use this to look for these juvenile shards. The lithic clasts are a little bit more difficult to tell apart, as they can be quite varied and different rock types. And if we see any juvenile material, then this could indicate that it's been an eruption at that point in time. So this would make it a target for our volcanic side of things. It might.
It's doing its best to see.
It could also be that there's some terrigenous input as well from these sediments as well that are on the land surface, which are rich in volcanic material. So this is why we look for concentrations and see if anything is kind of concentrated in certain layers within the core. So once this process is complete, we then move back to our description, add this into our detailed description. So this is layer by layer, and then grouping things together. It's detailed description around the grain size of the material, around the shape the sorting of the material we've collected. Really subtle changes in colour. So we've got, it's kind of like a paint chart. We've got you know, like when you bought a new house and you want to fix up your house and you go to your hardware store and you want to go through all the colour charts. We kind of use these things to agree over subtle changes in colour. Particularly for the biology, it can indicate certain colours can relate to high concentrations of diatoms or microfossils or phytoplankton, for example, in those cores.
And zooplankton.
And zooplankton as well. So yeah, this is when I was an undergraduate, I got a prize for micropaleontology, and I thought about doing that at some point, but yeah, now I'm learning a lot from everybody else here. I've gone more into the volcanic side.
Never too late.
It's not too late, no. Yeah, I got the flagellate part of that dinoflagellate right the other day, so it's still in there somewhere. Somewhere.
The
exactly.
importantly, the dinoflagellates here can cause a lot of pretty nasty blooms.
Okay.
Yeah, harmful algal blooms.
That's the extent of my knowledge. Yeah, so once we've kind of gone through these individual layers, we then we make a target for where we want to sample. So if we have an event layer, such as a tephra, a volcanic ash layer, or you know, this could be anything else that's got could be any flood layers or anything else that's coming in. We kind of want to see what the response to the system is before and after that as well. So if we have one of those layers, and the biologists and the micropaleontologists are doing some very, very detailed sampling at either side of that. That's one of the key aims of this research as well, is to see what the ecological responses as well to these volcanic eruptions. The volcanic eruptions that we're looking at from our volcanology side of things is really important, really, for three main questions. One being around the source of these. Obviously, southern Chile is full of volcanoes. The thing is with the timing of these, so this is important for the whole geological system as a whole, to see, you know, the timing for any ecological changes, but the timing of those eruptions for frequency patterns and hazards, and understanding long-term hazards from these volcanoes. And the third thing is processes as well, for the communities that live around them, so to see what the volcanic processes are, whether these are really explosive high energy events, whether they're predominantly effusive eruptions, which mainly produce lava flows, which are really destructive within their own right, but as a hazard and a risk to life is much lower than an explosive eruption, as things happen much slower, so we can evacuate communities quicker, and allow people to move away from these hazards.
That deserves some clapping. Get that worm.
Particularly from the glass and the fresh magma that is erupted during that event. So what we can do is we can go to the volcanoes and do lots of fun on-land field work, dig lots of holes and hammer lots of rocks, and take these back to the lab, and we can measure the chemical composition of these rocks and these layers. And from that, we can build up a fingerprint for that eruption or that volcano. So we have a kind of wider fingerprint for the volcano and a smaller fingerprint for each individual eruption. Sometimes there's a lot of crossover between these, so it's not always easy to tell. We have to use different methods, and you sort of get deeper into the analytical side of things, but quite often we'll have different chemical compositions for these layers. So then, once we've got that database and we've built up that work, with lots of colleagues here working at the Chilean Geological Survey and the University of Chile, as well as lots of academics that have worked across the globe on these volcanoes.
So we try one vibe call, please.
This database that's built up, we can then analyse our tephra and our glass shards that we find in these cores to match them to their individual layers. This is quite a careful process of extracting these glass shards. We put them into a really, really powerful microscope, which has analytical capabilities as well, which we call an electron microprobe. And this essentially fires excited electrons at the sample and can gather this compositional information. And then we can plot this up and see if it matches, and see if we can confidently identify the source, or have a range of sources that these layers and these shards have come from. It's argon dating is a really good dating method for tephra, but it's kind of relevant for things over 50,000 years in time. However, if we can't directly date these, we'll try and date any organic material in the sediment around the tephras, which is we can get radiocarbon dates, which are less than 50,000 years to pretty close to present day. We can get some pretty accurate ages of these carbon samples. And once we get those dates, we can effectively have a point in time above and below that tephra and extrapolate what we're assuming is an instantaneous deposition of these volcanic layers, as they're representing events that happen from an eruption, which might span several days, weeks, months, even years. But in terms of geological time, this is an instantaneous event. Things accumulate very, very slowly. We have just within since life began, in years of time, sort of recorded there, and the Earth is around 4.5 billion years old. So something that's potentially up to a year of an eruption would be recorded as an instantaneous event that gives us a directly sort of correlatable horizon within that. And then the third thing is looking at the processes. So this is looking at subtle changes within the ice that's melted and started to break up the ash and increase the fragmentation of that material. This grades up as we sort of move from a fine ash into a medium ash, into a coarse ash, which each have their own individual sizes of material, which I won't bore everybody listening about those different sizes, but we essentially get up to really large pebble sizes and big blocks, which on land can be size of houses or cars when we're dealing with volcanoes. In this case, we're kind of dealing with the finer side of things, so these subtle changes between sort of fine ash up to coarse ash, medium ash, looking for any layers within this, as this can indicate different changes in the pulses of that volcanic eruption. So if the magmatic flux of that volcano is increased or decreased, we see a waxing and a waning in the energy in that eruption. So if the energy increases, sometimes the hazards can increase. We can get pyroclastic flows, these hot dense currents of ash and rock mixed in with anything else that it picks up in its way.
That's good. So
trees, people, cats, dogs, anything. These are really devastating events. These contain various different sizes within them. But when they settle out, they produce different layers of different grades. And the same with fallout. So if we have an ash column which is transported by the wind, the heaviest stuff will fall out closest to the vent, and as it moves downwind, we'll get a sort of thinning of that layer, but also a change in grain size from something that's coarser to something that's finer grained. And earlier I was talking about the different components of the tephra layers, and these can include lithic clasts, or they can include glass and fresh magma, or they can include crystals. So the lithic clasts, these dense bits of rock that have been plucked up and thrown out of the volcano, they're heavier and they're denser than the lighter, fresh, bubbly magma that's come out of the pumice. So these tend to fall out quicker. Now in this case, if we've got a fallout onto water, we've got another added element in terms of this, that complicate things. We've now got water, so if we tip any of the stuff into water, obviously the properties of the water are different. The settling velocities are different to air. We have a different rheology in that water. So we're getting the heaviest, densest particles and things also still settling out faster and falling as a layer towards the bottom. But we also have the element where if you've got lots of gas and you've got then they can float on the water for a while as well. So I was just working in the lab on an eruption layer which we've seen, and that had a very coarse base, coarse ash base, which was mainly comprised of these lithic plasts of this material which had settled down quicker through the water column. The main bulk of that eruption was then a sort of medium ash, so finer grained, but you know, kind of like a sand sort of grade that you'd get at a beach, and that was settling after. But then on top we went back into something which was a bit coarser again, larger grains, and they were more of these bubbly clasts which had been floating on the surface of water until all that pore space had become waterlogged, and then they'd settled out. So you kind of get 3 points in time that is recorded in these. So it doesn't necessarily always reflect the points in time that are happening at the source of that eruption from that volcano. So water and these samples from a marine environment can be really complicated by that, as well as having currents, as we've seen on the images now. You know, we have other material which is there as well. You know, you can land on quite an irregular surface, or you know, it can be biogenic material or animals and burrows and things that are happening that move sediment down. So there's a very complex sort of relationship that we have between different layers within the core, essentially, when we pull this apart. So hopefully that's kind of a bit, kind of gives an insight into what we're doing. Once we've got these samples, the next sort of step is lineations or ostracods or foraminifera, or really small microorganisms that are then included in our sediment. So these samples, after they've been taken, are then logged very carefully in terms of what they are, which layers they're taken from. We dry them out in an oven if they're particularly wet, or if we want to do some form of analysis on them. Here we have on board, we have a handheld, what we call a PXRF, stands for X-ray fluorescence. We often analyse this in a lab back in universities or research institutions. It's quite an expensive piece of kit, but it allows us to get these detailed chemical compositions of layers as well, similar to the electron microprobe I was talking about. It's just another method. Whereas there has been a piece of kit which is really neat. It kind of looks like a sort of laser ray gun or something from a sci-fi film or something from the late 80s. You can point this, you can take this into the field at a rock outcrop. You can point it at the rock outcrop, and it can gather a general composition of those rocks. It's not as detailed as the analytical method that we'll do later on, but it can give us an indication of whether things are giving a similar chemical signature or a different chemical signature. So once these samples are dry, we've got a handheld one on board which we can all point this laser ray gun essentially at the sediment. Takes around about a minute or two for the analysis to be collected. It's completely non-destructive as well, so the sample can then be used for other analysis, and it hasn't disrupted anything in the sample, which is great, and exactly what we need to have on board. And within this we can start to build a general chemical composition for these layers, and see if we have two layers that are together. We can see if they're producing a similar signature, which might be that there's been an eruption where this stuff has been deposited on land, and there's been then a flood event or a lahar, or it's been surface runoff which has brought this material in. And often we can see that where we have the same eruption layer is recorded as several events within a core section, because of successive washing in from these events. Whereas, if we can see that there's a different chemical composition, volcanology is great, and the stuff we're doing is very interesting, but it's also a very applied areas of science where the majority of people that live around volcanoes, and it really in a time of crisis, it doesn't really matter really whether we're getting these subtle changes in grain sizes and all this amazing science that we can do. The kind of answer we want to know is, will it impact people's lives? Is it potentially harmful to people and cause loss of life, or destroy
Yeah, of
people's
course.
livelihoods.
Is it the gate?
And that's the kind of the main driving force, I guess, behind volcanology. It's quite an applied area of geology.
The gate in the.
So we can use
No,
this
I
then
didn't mean that. I meant
to
the-
essentially
so
move
there's a gate
forward
in
from
the-
that point and to build into, you know, all of this stuff kind
Is
of
that
pulls
currently
together.
blocked?
So we'll
No,
have
okay.
the time element of these eruptions, we'll have the processes that are happening, we'll have the volcanoes they're from, and then we can build this into a hazard perspective. So some colleagues on board from Min, which is the
We're off the
Geological
seabed.
Survey, are doing some amazing work on hazard mapping these volcanoes. Yesterday they gave a seminar to all the science group and the crew on board about all of the amazing work they do.
I don't
How
think
they
there's
go
anything
from
in
these
full yet.
decisions from
I don't think. Yeah,
you
I
know,
think
sort
that
of
pile would have been thick enough to.
mapping
Yeah.
out these deposits on land, turning this into a map which then shows the distribution of these deposits, as well as adding in the
Just gonna
modelling
bit down.
and various other aspects of volcanology, which
Oh, some
sort
fish.
of incorporates some fish. I've seen any fish for a while.
Yeah.
Do you want to talk about what we're doing right now?
Yeah, can do, yeah. So, just have a break from volcanology talk. So at the moment we're just, we're basically, this is one of the
Okay.
vibrocores from
Yep.
the samples I was talking about we're taking. So we're just pushing vibrocore, vibrating this into the seabed. So
That's
this was
good.
developed just for this,
That's great.
this research expedition. So this has been the first few days that we've been testing this, and we've been getting some really good results. So this vibrates down and pushes a core barrel through the sediment, and it's got what we have called a core catcher at the base, which allows them to. We basically collect this sediment here, and sometimes we don't get a full recovery. Sometimes we'll get half a recovery. Sometimes we might only get 20 centimeters, but the aim is that we will push this down as far as possible to get as much of that preserved stratigraphy or layering within the set. Each has got various different levels of data which we're looking at, and I'm checking all the time talking to you. So I'm looking at one screen now which is looking at the vibration intensity, which we've got control over. It's looking at resistance in the sediment, which we're noting the whole time. And we can record these in our notes and logs and compare to the recovery we actually see compared to what we're expecting to see from inside the ROV operation room, mission control room, as we're calling it. And now we're rising the vibrocore back up, so this will now be hopefully full of lots of that material in nice beautiful layers for us to come back in. Occasionally we have to move this around, so the crew are experts in all of this. They're steadier hands than heart surgeons, I guess. So yeah, you can see the vibrations on the screen. Pushing back down.
So,
We're coming down slowly into the sediment. Yep. Sorry.
so Seb and I are excited because we thought that there was something hard that we were hitting with the push cores that we might not be able to penetrate with the vibrocore device. But as you can see, this is the whole reason why Seb worked very closely with Schmidt for quite some time to make what you're seeing here a reality. The vibrocore is meant to get into these sediments that are maybe a little bit harder to penetrate, that you can't just push into, that you actually have to vibrate the sediment to make it act more like a fluid, so that you can push this metal tube in. And so we're both very excited because what we're seeing here is that we were able to go deeply into the subsurface. So whatever hard unit we were hitting with the push cores, we went past. It should be in this core barrel that we're shaking right now. We're trying to get as much as possible, so we're just going to continue trying to push it down as far as we can. And maybe we don't get the lowermost intervals that we're probably contending with right now, but we might get a little sample caught on the bottom of the core in what we call the core catcher, and that can be very useful information to understanding the geophysical data that we've been getting back, looking at the structure of the seabed and the sediment layering below.
Okay, brilliant.
So we could be penetrating much older layering that might be glacial in origin from about 20,000 years ago when we had a kilometer thick ice sheet here in Patagonia, the Patagonian ice sheet. For reference, the West Antarctic ice sheet is 2 kilometers thick and the East Antarctic ice sheet is 4. But of course, that is changing as we speak, thinning and accelerating at the margins. Was it hard to pull up?
Yeah.
So, yeah,
Okay,
so these
so probably got stuck
vibrated
in
a little
something.
bit on the extraction.
Perfect.
So, cool. Yeah, and then it's coming up smoothly.
Okay.
I imagine this could be quite heavy. Well, I hope it's quite heavy. Because we had some surprises the other day with these gravels that we really struggling going in a long way, but struggling to
Yeah.
recover material. We'll see. I feel hopeful.
Yes, I'm hopeful.
Yeah, this is needed.
I think
If you
we'll see how the teeth perform.
Yeah, so these changes in size of clasps as well, they I mean, this is a really good method for the vibration to try and recover as much material. Occasionally, even with drilling, you can, when the change in density happens, essentially the recovery can stop and you can kind of break along these boundaries, so sometimes you don't recover as much material of these as possible. So hopefully we can recover as much material as is there, and really it is a case of trying to record as much information as we can here in this lab, and then comparing it when we split these cores open and seeing what we get, which is really exciting part. Unfortunately, that's not live stream, so you can't see that, and that's where I am most of the time. Most of the time, not really in this control room as I'm working through all the samples. Yeah, we've got a good production line, I guess now, within the lab where we work through in order through these different steps, and as we get more and more samples, it means there's more and more work to do that comes in, and if we fall behind, which we try not to do, then there can be a backlog of stuff, so things get very busy on our end back in the labs here. But yeah, I mean, this we then will compare this and use this for planning as well to go forward. You know, if something seems like it went really well in this ROV dive, and then actually our recovery is not so good, then we have to alter things. We have to try and adapt, and you know, we're learning this as well. You know, as I said, this is a new piece of kit that's been developed just for this cruise and will be used going forward. And as with anything, you always have teething problems at the beginning. Yeah, we can certainly see that from the first few cores, we're improving our recovery, our splitting. We're getting much better results now. But obviously, this changes quite rapidly. You know, going into softer sediments as well. Yeah, for anybody who's watched a few of these dives. Yeah, quite visibly, strikingly different. We all get quite excited. And we've got this is live streamed all the way across the whole ship. We have screens in pretty much every room, multiple screens, which we can bring up anything from cameras around the ship to data from anything being collected through to any of these cameras. So we're a bit fortunate. We have access to a few more cameras than you guys at home. So we've got multiple different angles and perspectives. We all get quite excited when we see the seafloor for the first time, because we've been looking at the seismic lines, we look at these chirp profiles, and the mapping data, and seeing some really interesting features. And all of this planning, then, you know, it's our first peek at the seabed, and yeah, sometimes it's full of marine life. You know, big fish
One more.
away the cameras, or little fish, cardboard box, or we have sometimes we have lots of pebbles on the surface, or lots of sea urchins. Sometimes we see it's visibly very, very clayey, and as we land the ROV, Sebastian lands down for the first time, we see a big cloud of material come up, and other times we can see it's quite sandy. So these upper few millimetres and centimetres really of the sediment are also really, really important for just the modern day processes, for tying this all in with our understanding of terrigenous input, of you know, fluvial systems entering into the marine environment, yeah, we have we basically have this first few centimetres is if we have a historical eruption such as the Chai-10 2008 eruption or the Kalbuka 2015 eruption. Essentially, we would expect to see material from those that is settling on the seabed. So this might not necessarily be preserved as a layer, but hopefully in that first 1 to 2 centimeters of sediment we have. We have some shards from those eruptions, so we're always sampling the top and doing a high resolution set of samples from the top to A, understand the modern day environments much better, and B, to then try and find any sort of events that we know from historical observations. We have lots of data from on-land records to try and correlate into the marine record to give us a sort of higher resolution and understanding of what does that marine environment look like as a comparative sort of product compared to our on-land records. So
do that, and then
so the arm now is just mounted onto the base. So this core catcher is holding this material now in place. That should be secure. The arm will be turned now to secure that, so if a current or something happens, it doesn't knock it over. So we've successful. There we go. It's all been turned. So successfully secured. For anybody who's just joined, in the foreground we've got these orange cylinders at the top. These are these push cores which collect the upper part of the sediment.
we got it in.
Do high resolution.
Claps all around.
Exciting.
Yeah. So
Cool. So we do repeat.
we're gonna do a second vibrocore here,
Okay.
and hopefully we will punch into that harder unit again. Get past this soupy, muddy stuff on the top, and we'll get a sample hopefully of what's below. Of course, we are changing things on the fly as we are moving along here in Patagonia, in this area just offshore Chai-10. And so one of the cool things, hi, hello, buenas to la gente de Concepcion. We're very close to y'all. Yeah, woo. All right. We love that we have local Chilean viewers.
Yeah.
We have about half of our science party is here from Chile. So very proud of that. I don't know if you guys know this, but Chilean geologists are some of the best in the world, and Chilean biologists, because we have some of the most diverse geology here and some of the most diverse biology. So we are working with the jiggly stick here with the vibrocore, and we just collected one, and we had some pretty cool hard units just below this clay that you're seeing here, this mud-rich unit that was full of life, full of infaunal organisms, mainly worms. There was a big annelid worm that bounced around, but we finally got it in the bag. We'll bring it up and maybe we'll post some pictures later. But the biologists here want to study that from the Universidad de Valparaiso. That's one of their key studies that they're doing at the seafloor here. But for geology, we really want to understand the layering of the units. We're looking at the clay at the surface. We're trying to get a second sample with the vibrocore, with the jiggly stick, trying to penetrate the lower. That's really what this is meant for. That's why this was built. So do you want to sit back in the left seat?
No, you go ahead.
Okay.
Yeah.
Yeah.
That's what when you want.
And we get multiple cores, you know, as many as we can, so we'll get 2 here, to basically compare, and we archive one of these cores where we can then scan all the way through, and we can also split the cores, and we can then get a half where we can sample and a half that we can archive as well, which can be further sampled.
And the greediest samples on board sample people on board are from the University of Alabama.
Roll Tide.
Because we need more volume. But we're getting sample. But we're also trying to test things. We're changing what the bottom of that core tube looks like. We call it the core catcher. The ROV pilots call it the aperture. It's just where it opens up at the bottom, where we're pushing it into the sediment. And hopefully, when we pull up after pushing it into the sediment, it will hold all of that sediment there in place so we don't lose it. So now we're deploying the second vibrocore tube, trying to get it off the rack. Just got to a nice location here offshore the Rio Blanco, where we've got quite a bit of mud on the seafloor. We like mud, don't we, guys?
Yes.
Oh, yeah.
Yes. Any kids listening? If you like to play in mud, get dirty, make mud pies, just keep doing it. You can make a career out of it. There's a whole group of people here, including myself. We get paid to play in the mud. And the mud can tell you a lot. It can tell you a lot about the history of this area. Volcanic history, the history of life here, how it responded to volcanic events, how it responded to climate events, oceanographic changes, you name it. Mud is the method or the material that we use to apply different methods and tell the story, tell the history of the area. So we're all just like storytellers that really like to play with mud. Is that right?
Yeah.
Yes.
Yeah.
And who you were hearing from just a minute ago is Dr. Ali Hodgetts.
Ali Hodges.
I'm just calling him Ali. He doesn't get a choice. He gets a nickname for me. Everybody gets nicknames.
What about Jacob?
Jake, I know, I was just staring at Jacob.
Jake. Call you Jake.
Jacob, bye. You come up with a good one.
Just like
Diatom Whisperer.
Maybe. I like that one.
Mane looks jealous, though.
can we get our own?
Okay, so we're going to start shaking this vibrocore. What's that? Oh, yeah, did we pick up and move over? Oh, yeah, sorry. Oh, gosh, sorry. Me talking about nicknames.
Have like huge tree cuts outside.
How far over do you want to go?
Just half meter, just local,
I'm down.
just to get out of the way of the previous.
Yeah.
Go back.
All right, so we're just picking up and setting back down to get a fresh surface since we played a lot in the mud right there. Took a bunch of push cores, 5 push cores, a vibrocore, and 4 scoops. So chased a worm around.
Okay. Punching down.
It was called James.
Oh, the worm's name is James. For a minute there, I thought it was going to be more of a Jamestown worm, because he wasn't looking so good for a while. But we got him in the bag. We're going to bring him back up.
What's he called, James?
The chap named James, I think. Wasn't
We
it?
did not name him. We're pushing into the sediment now. Did you get that scallop on the seafloor? The like open scallop shell? We've seen these pectins and scallops, some of our earlier sites, but they weren't as muddy as this. Kind of interesting. Of course, that one, I can't tell if it's alive or not. If it's just a one valve of a shell, it might have been transported here. Okay, so we're vibrating.
Everyone's liking the jiggly stick.
So we're getting a lot of resistance on that. I think we hit something hard. Like maybe there's just a couple clasts here. Should we just pick up and try again?
I don't think we've got anything there, right, really. We can just see. How far do you think it's gone in? Do you think it has already gone in that far?
Maybe this far?
20 centimeters.
Further than that?
Can we try it?
Top of it, the check valve is below the, it's below the cross piece. So it's a 2 meter.
So what would you
This is a 2 meter, yeah.
Right, a few tenths of centimeters.
2 meters, you got that? What if we stop vibration and then start again? Since that worked. The site that had the cohesive clay.
I don't think we can pick up and go again, right, if we've already got.
Yeah, I wouldn't do
We
that.
knows then how we can.
Yeah. But just stop vibrating here. And just turn it off for a moment. And then turn it back on.
Yeah.
That's not helping. Okay.
No, you're fine.
Do you want to change the vibration or call it?
So sorry, I mean, how much do you think we got in? Like, anything? Or is there a way to
Well, just looking at this, it's all the way up from 0 to 20, so we're at least 20.
We're at least 20 in, okay. So we can't reuse this, right?
If we were going to, it would be to test the core liner and catcher
Yeah.
meters. We've already got that with the push cord.
So that's
True,
what I'm
true.
at least 20.
So if you want to
Yeah,
test
at
the,
least 20.
Okay, so as long as we're really
Probably
clear
more than that,
this
but
would,
that you can't use
that we
this
can't
one.
use that upper, we
Yeah.
can't use the top
Can't use the top of it.
20 in liquids.
Is that
Maybe
another
we'll
crib?
test, I guess.
Yes.
Yeah.
Because
Yeah.
this isn't going to add anything to the science.
It's not going to add anything to the previous
Yeah.
one anyway.
Yeah.
Okay.
So it would be to test the core catcher and
Okay,
the
so do
liner.
you want to try just slightly to see?
Yeah.
It's obviously, yeah.
We want to pick up, move over just a tad to get a fresh surface and try again.
But can we remote really clearly that we've done this?
Do not
We
use,
cannot use this. Yeah.
this is more of an engineering test.
But we can't have to sort of compromise. That makes sense.
So now the question is, we have.
So what are we testing, Becky? Just
Let me grab it. We'll come down to a certain amount, pull it up, we'll be able to tell you exactly how much.
we see how far we can get.
So that's
Yeah.
20 degrees right now.
obviously the issue we've had before is we can't.
This one get marked. I was marking the tubes where the clamp, where the lock, and where the quiver. Or,
Yeah. You can look in the top and the bottom of it. Which is,
Yeah,
we lost
we want to
one.
look at the bottom of it.
Yeah. Yeah.
It's the best we can do.
You can see how thick it is. You can estimate the sediments from the top and bottom. But yeah, this won't add anything.
You sure we want to go in again?
I want to know if the nylon liner is useful or
I mean, I
not.
guess it would add something. If we could get in again, we at least know what there's something at the bottom.
Yeah.
It would just be a floating
Yeah.
stratigraphy.
Yeah.
But at least it would tell us what's in the other one,
Yeah.
which is useful knowledge.
Yeah.
So yeah, okay.
And even if we have repeated at the top, we could use the bottom, even if we opened it.
No, exactly.
Yeah.
We just have to be very,
review,
very clear on that.
Yeah.
Oh, no. That's good. Okay, winching up. Slowly. Another 5.
Yeah.
15.
The currents are actually better today than they have been in a long time.
20.
Not considering that, when do you think you're gonna wanna come up?
Jesus.
We would like to
25.
so we'd like to ideally probably up to
So we'll call it 30 plus 20. So that was 50 centimeters.
57 meters?
50.
7.
50
Centimeters.
50 centimeters.
50. Thank you.
You can see the tube just cleared the base. So maybe.
So more like 45.
yeah, so
Okay.
it's quite a big transfer.
Perfect.
We'll put a tilde in front.
Okay. Here's the tilde.
All right. So what's the verdict?
I still want to test the aperture there.
Pick up, move.
Pick up, move, and try. Yeah, core again.
Near enough to see, then to see.
All right. Moving over. Surface corrosion. Increasing over there. Move.
Hey, Ollie.
Perfect,
Do it like a
perfect.
couple of hundred
Yeah,
meters
this
straight.
is good.
So we'll be doing some moves. Can you guys keep a really good eye out for any kind of fishing floats?
Okay.
All right.
Let's see, watching down.
Okay, thanks, sir. Yep, just let it go and see anything. Bye.
All right, so what you're seeing us do here is we're actually probably not going to use this core for any of the detailed reconstructions we just talked about. We're trying to test what works best here. So we've been playing with the bottom of the core catcher or the aperture to see if we can get better sediment recovery, because there's many places where we pushed it all the way in and yet we come up with near empty barrels or just partially full barrels. So we're testing out a few things here, trying to figure out what works best. And right now we're just moving over, even though we already have some sediment in this core filled up, I think about 45 centimeters. I think there's a hard unit below that we might be able to penetrate better here if we give it a second try and see if those modified bottoms of this core tube will recover it better. Let's see. It's okay. This is like a survivor core. This is our Rambo core. It's been beaten up a little bit, but we're gonna try to keep pushing it in.
Let's go grab
We're ready for vibration. How many times do you hear that every day? All right. We're getting ready to get this core tube into the sediment so we can get all the layers below. No rotation on the bit. Thank you, William, for your question. There are coring types that we can use a lot of times on land, but also, you know, in environments like this where we're actually rotating the core barrel, and we have a bit on the end that cuts into the bottom. But here we're not trying really to get in through very deep, hard, lithified sediment units. We're mainly sticking to the recent, which is unlithified. So we're not drilling. We're just coring with a barrel. And in this case, we've done pushes into the sediment, and now we're vibrating a metal tube to see can we get a little bit deeper. But we're not drilling at all. We don't have any rotary drill coring happening here. But you can do that. We've done that quite a bit around the coast of Alabama, the rotary drill core. And of course, if you are operating offshore with IODP, International Ocean Discovery Program, which they're having their very last expedition as we speak, unfortunately. Hopefully they will revive, but they use an actual drill bit and they go very deep. So we're talking hundreds of meters into the subsurface. And of course, for oil and gas exploration, you can go much, much deeper. You have a riser on that well, basically holding back all of the things that you don't want coming to the surface from the subsurface, doing it in a controlled way where you're not affecting the environment. This is very shallow coring, so we wouldn't encounter any fluids like oil or gas in the subsurface here. We're just basically scratching the surface. And of course, we're looking for very recent sediments. It's not going in at all. Okay, so we have certainly hit something hard because as much as we try, we're not getting any penetration here. So what should we do next, Seb?
I think we finished this one. I mean, we may have just hit the right spot with the first one.
Yeah.
And we got a good call there. We can open this and still get some understanding of
Okay.
what that base is.
Okay.
So, and then I think that trend segment
To the west
to
and then-
west.
Okay.
I'd say for about 200 meters.
All right. So pack it up, boys. All right. Gonna put this back, and we're gonna take a little trip. We're gonna look at the seafloor as it varies in a little box around this region, because there's some really interesting features that we've seen from the acoustics and mapping this area overnight. Yep. So some of the push cores that we pushed into the subsurface, they hit something so hard that it actually pushed up the ROV. And the ROV is like 9,000 pounds when it's out of the water. It's a little bit lighter, but not much lighter when it's in the water, so it's a pretty substantial surface that we hit.
First call's good.
See what we've got here.
They sealed.
Okay.
Here. I've got card stuff that far, but
You can push past them.
Yeah, so we can think of this in two ways. It is kind of a bummer we didn't get deeper sediment, but at the same time, we're learning something. Even the absence of material that we expect to find is still data that tells us something. So now we know there's a very hard surface. We were just very fortunate, it seems, to get the first core that we did. We might have been in just the right spot to do it.
it's parallel that did. quite a big scale. And it's
Okay. Well, we're almost clear. Well, just if I open it
it's
right
like
now.
this sort of character. Whereas this is more sort of finely layered.
I guess the darker bands here that
You know,
tend
obviously
to be more
we're
competent band.
again the very top of
Yeah.
this as well, so it's hard to.
Yeah.
It's pretty hard to know exactly what
So
we're
you
into.
think
You know, on the scale of this, we're a black line. So,
Yeah.
you know, meters penetration, so it's really hard to know what. But I think we may get some insight. Backscatter patch. This one.
Yeah.
We'll see. Maybe if it's big inadvertently, we'll get a view.
maybe when we look at what's in the core catcher, that's a good core, we can see if that's glacial.
Hopefully we can at least get a
Yeah.
an insight.
Because
I mean, actually,
it's-
that's the one with your more flexible teeth, right?
Yes.
Which left a bit of a hole. So
We can.
Yeah, that's
We
true.
just do the top and bottom again, like we just did.
But yeah, we get to see, does it look like diamond?
is it
Because
this
if it is, that
diatomaceous
tells
clay
us-
that you had? It could, this and that.
It could be,
Yeah.
it wouldn't be subglacial, it would be proglacial, but like proximal.
Yeah, that paper, right? I was looking at that was the clays were fossiliferous,
Yeah.
and then they were moved over.
Yeah, it's pretty common. Glacial marine sediments. There's
Why
some
would-
examples of that.
Why would it be pro-glacial?
If there's diatoms in it.
On top or in
In the mud.
the mud?
Yeah, it can't be subglacial. Glacial marine, or like I was saying, reworking, but there wasn't a lot of evidence of abrasion for those fossils, so they were broken.
There is some
Oh,
expected
whoa,
lots of
whoa.
which is good.
Huh. Okay.
So we should have a good core catcher. Well,
All right. Okay.
still a complex core because of what we did with it.
We are very excited because you can see there's some materials sticking out of the bottom. So we might have punched into whatever that hard stuff was and brought some back up with us. It got caught in the barrel, in the bottom of it. So we'll learn, even if we can't open it up and have perfect layered units, we can learn just from what we sampled in the deeper part that we pushed this into. That was kind of hard, that where we stopped. A lot of times when you take cores, you bottom out in the hard units, and you only really know anything from it from the core catchers. This is why about 20 years ago now, they built, they actually drilled a hole into the drill rig to do shallow drilling into subglacial deposits that are very hard like this, so we could get better samples of that till. Because all of our cores would just land in the till, and we'd only get the stuff on top of it before then. Okay. So we're pulling the rack in, we're kind of tidying things up here, and then we're gonna go on a little sightseeing tour. Isn't that right, Scott?
Hopefully the visibility is.
Yeah, it's not bad here.
Okay, so we want to go west for,
And looking west.
looking west for how long?
Let's see, about how many meters to the west? You want to say like 200? Can we do 200?
We
I
need to
don't.
move
Yeah.
ship and stuff, yeah. This is
I thought it was more like 50. So 200.
The scale of these squares is about 300 meters
Okay.
across the square. So I
300
just think we wanna
meters.
Get
out.
well across.
Okay, get well across that, and then we'll go north, looking down. Are we gonna try and map, or we're just gonna watch it from the camera?
I think we'll watch it first, see if it's interesting, and then
Okay.
if we see like a real feature, then I guess we could lift and map it back.
Okay. Okay.
I'm just going to double check and measure across this.
Okay.
So you check that.
Okay.
Okay.
Good.
Going west.
Bridge, RV. Yeah, it's an updated waypoint, please. Point 3, point 4.
Yeah, no, we just.
We just want to see this seabed, but we don't have to go super slow. Might slow down if we see something interesting.
Point 4 is
Huh?
the point 4.
Okay.
All right, shit just started. Okay.
Yeah, that's right, Becky. This,
You guys ready?
We are
This
we are
is-
ready
this
on
is
this
like
side.
100 meters wide, this feature.
Okay.
So we do need to move on the order of sort of
Okay.
200 meters or so
Okay.
to get across it at least.
Okay.
Yeah.
Okay.
So is that?
200 meters west, 200 meters north, or 100 to 200.
Yeah, let's do
meters
200 meters west, 200 meters north first.
Okay.
Which in theory should get us off this feature and then back into it.
north. Okay.
And how close can we say seafloor? Can we stay close enough to have visibility, or is that?
Yeah, we'll
Okay.
see. Let me get out of this mud cloud first from lifting off. See what we see. That's, hard to see.
Mm-hmm.
Yeah, even that would kind of.
Okay. We don't have very good visibility because there's a lot of particulates in the water.
What did I do? How did that happen? Could have sworn I turned.
It was the other one.
Was the other one? Oh,
The
southern
other
hemisphere.
west.
The southern hemisphere.
We went right. We should have gone
You need to print out your MapQuest directions. That's what I have to do sometimes.
Bridge, ROV, updated waypoint, please.
Updated waypoint.
Look at all the little krill. I love how they have these two big black eyes that are kind of close together. Kind of silly. Whoop. Kit Kat. Oh, I can't. Copyright issues. I'm having a random chocolate bar.
Thank you.
Mm. We did so much work to go get this. All right. What we should really be eating is popcorn, because this is... Oh, look at the seafloor there. It's kind of similar. Looks like there was a clam, a bivalve on the seafloor. But more or less the same. Oh, what's that? Ooh. Can we Got a sea pen. Had some kind of coral or gorgonian there attaching to a boulder. You know, we might have just hit a boulder or something. A large clast. We were trying to vibe record.
These volcanic deposits where these rocks are sort of hard substrates that get colonized. So you're going to see them.
Fish. Got the fish? Yeah.
You get some isolated rock. It's covered in life.
Another fish. One looks more like a classic bottom dweller. Kind of flat shape to it. Ooh. Coral of some kind. So any little boulder or large clast, it seems there's some sessile
It's an interesting question.
organisms.
Where these
Just
come from as well.
yeah, where do they come from? Why are they here? But anytime they are here, it looks like there's organisms that are just attaching to it. Quietly chewing chocolate. Are we going in circles? Looks just like it. The sea pin to the right.
Don't put it past me.
Oh, look, there it is again.
And again.
Wow, and the sea pin. Okay, well, we're getting an idea of the benthic assemblages here. Basically, nothing but mud and worms, happy little worms. And then on occasion, some boulders with corals, maybe little sea fan-like gorgonians, not really sure. And sea pins. These are long, white little worm-looking things sticking out of the seafloor. It's always on the left.
Yeah.
Huh. This is interesting. Maybe. Oh, there we go. There's one on the right. But again, the same assemblage, the same group of organisms. Another sea pen there. It's lucky because the biologists, if we had any empty scoop bags, it would be a goner. Okay, here we go. More of the same, these kind of deep corals, isolated. There aren't too many of them, just sitting on boulders. Might even be some echinoderms sitting on that. I couldn't really tell. We'll have to go back and look at the footage later. Yeah, these
Almost 100 meters. So
100 meters now.
Yep.
That one had some corals in a clam, bivalve. Okay, here's another little site.
Go for another 100. That's great. The isolated blocks at the minute, but that, yeah, if we were pushing down into one of those.
Yeah, if we were pushing into one of those, there's no way we would get anything back. So
So I think we go, yeah, another 100 back here and then land.
okay.
And it'd be great to look at one of these in detail, right?
Yeah,
You know, maybe then there'll be more of them.
more of these boulder type harder surfaces. There's a set of them. And these corals that you're seeing, the kind of pinkish looking corals, well, they're not really relying on light, are they? Because we're too deep here for them to get much light at about 140 meters water depth. So they may be getting their food other ways, not in, collaborating with the algae, but instead making use of these nutrients, of which you can see there's a lot of nutrients in the water here on the seafloor, floating in the water. they're sitting next to some other filter feeders, so that checks out. Wow, this might have a sponge there as well. More diversity in the corals. Oh, I see the star?
No, I got it. You asked. I picked it up.
Maybe a star and an urchin there.
Well, that's what I'm saying. Is when we stand, there is pressure.
How many meters now? You gone?
About 100 and almost 150.
Okay. Like there was another one to the right there. Guess we have to be careful where we sit down. Not be on one of these rocks, boulders that are sticking up. All right, so we're just doing a little square here. Right here. Making special requests. The ROV pilots here to stop where we see something interesting
Wherever
and
our Pigpen dust cloud is.
yeah. So you can see it's very muddy, the seafloor, because anytime we are moving the ROV, turning on the thrusters, it's gonna kick up a bunch of this mud. That's why it looks kind of smoky.
Okay.
Who?
Oh, that was him.
Sorry. I didn't realize this would pick up so much. I was just interested, Becky, that block there had a lot of scour around it.
I didn't see the block. I missed it.
The last block we went over, like it was scoured around.
Okay.
By currents, I just wanted to expose what it was on.
Okay.
There's clearly plenty of fine stuff around.
Mm-hmm. The krill are happy. So we were moving the ROV about 0.4 knots. Yeah. So not too fast. When would we want to try? I guess guess depending on what we see here, do we want to try the multi-beam again?
Yeah, I think we should move northwards visibility
Yeah.
first. And then maybe. Yeah, still kind of want to go on to what we think is that banked feature as well.
Yep.
Maybe we can go for these ones there.
Ooh.
That's really good. Okay.
Setting it down. Oh, wow. Wow.
Pretty solid.
Zoom in on.
It feels solid.
Yeah.
This looks sort of stony, right? You can see in a sense when that's cleared.
Try to get little thrust as possible.
Very careful operation. Trying not to kick up the mud.
Current might be going a different direction now.
Okay.
Doesn't look like it's shifted.
Okay, we're waiting on it to clear so we can get a better picture. Diego, did you think that was another Gorganocephalus?
Yeah.
Did you think that was another echinoderm Gorganocephalus, or did you think it was a coral? When we look,
So over in the
the
sonar,
pink.
we were approaching some striations.
Okay, basket
This
stars.
is
Yep, yep,
about
that's what I thought.
15 meters out right here.
Ahead of us.
Ahead, dead ahead.
Okay.
And we were about 20 to maybe 30 more meters left
Yeah.
on our 200 meter move.
Okay, so could we,
Because, so here, so this is where we started.
yeah.
That's 100. This right about here would be 200.
So we let this get clear, and then, yeah, we go ahead. So what do we have feature might be?
Yeah, so it looks like our current shifted. I have very little thrust pushing us down just to keep us in this spot. For example, here's 0. So
This is just a local.
I don't have the tether pulling on me. This is just us waiting for the dust to clear. And hopefully we're not wiggling. I want to put a little thrust on just to hold this in spot. But that's
Are we on
going.
Are we on seabed?
We're on the seabed, yes.
We're on the seabed.
Yeah. So this thrust is just going up into the air.
He said it felt very hard when he sat it
And it
down.
was very a positive. We are on bottom, not like squishy.
Mm-hmm.
Yeah, it's interesting. So more so than where we landed before, Scott. So
Oh, yeah.
a different feel.
Yeah, and even as we were going, and I was trying to get my altitude so we could see, there were times where the front, what I record, the gate part was plowing.
Oh,
mud.
yeah, yeah.
The first site.
And as we were transiting
As we were transiting.
from here, it was plowing mud every once in a while while I was
Yeah.
trying to adjust my
Okay,
altitude.
and now it's not.
And now, yeah, there's
Right.
This
So
is,
I think we've crossed this change.
Oh, it's starting to clear.
We've crossed this change, but it's not because there's a fine amount of mud everywhere. It's sort of visually not easily obvious.
Yeah, this is just a fine layer of sediment. It looks like.
Yeah.
I just tried to put my cursor down there.
Yeah.
Oh, there's
so
the-
now, so now this is all
Yeah.
rock with sediment.
Okay.
Mhm.
Yeah,
Not
that's
mud.
really useful.
And this is another Gorganocephalus. That, just like the one we
yes.
pulled up,
Yeah.
basket star.
Yeah.
It's an echinoderm. Apparently, it likes this environment. This is the one that we pulled up the other day was a Gorganocephalus chilensis, so endemic to Chile.
Oh, really?
Yes, and so this looks just like it. Of course, we'd have to bring it up and look at it to really
Actually,
confirm that.
It was in.
It was in,
lithologically
similar
environment.
environment.
Do you think you can zoom in on some of these?
Mhm.
I get a sense it's quite pebbly again, right?
That looks like a sponge there. And then maybe that's a coral up there.
That's got
Stars.
Looks like 50 meters.
Yeah.
There's an awful obstacle. Get together, get hose up.
I think whenever we see like the organisms like this on the seafloor, that probably means that there's a hard substrate right underneath.
Yeah, exactly.
Yeah, that current deformation. So now, before the current seemed to be coming out of the west, now it's kind of clocked around, and now it's blowing, unfortunately blowing north, and that's the way you want to drive eventually. So
After
it's
this,
going to be tough visibility-wise.
I mean, I
You're
think-
going to have the current pushing all the dust up into you.
I think we have a sense of what we're expecting, which is that when we drive north, we'll get back into
Bridge, we are in position.
You want to sit here?
ROV copy, thank you.
just.
I'm just eating chocolate.
Oh, is it that?
Yeah, you can have this. I think you've earned it. Okay, you got one too. I'll miss you. This is for you. Okay.
Diego, you see what you want? Do you want to zoom in on anything? Do you want to sort of get closer features on anything?
Okay.
To the east of
Let's see. That is
these down here, thank you. Down.
this part here.
Yeah.
I think he was pointing at this. That looks like an anemone.
There's a crab on the sea across.
Where is that?
Down here, that
Oh,
camera.
yes.
It's feeding. On the top right.
Oh, I see it now. Nice. Oh, I can just look on the screen. Very cool. There's a lot of life here.
I think those are animals.
I'm going to send this to my friend who is a decapod expert, the Alabama Museum of Natural History. Shout out to Adiel, my buddy, who is a paleontologist who studies decapods, crustaceans like this crab here. But it looks like we've also got another basket star to the left of that crab. Ooh, look, the crab is moving now. It's moving to the right of your screen. But then that largest creature living on that rock there is a basket star from Chile, endemic to Chile, Gorganocephalus, like a medusa head. Chilensis, Gorganocephalus chilensis. We confirmed this when we brought one up a couple days ago from very similar seafloor setting. We've also got some scallops, pectin. It looks like there's a pectin there, a few of them. And that's a coral. That's very clearly coral. Oh, is that a worm? Okay. This is Diego, who's a grad student from Universidad de Valparaiso, looking at the seafloor. We're zoomed in here, as you can see in your view. We've got a coral in the lowermost part. It's kind of whitish in color. Oh, the sea star is moving. You can't see it in this view. It's in another view. There's a sea star moving. We've got some shells that look like pectins. We've got some worms kind of sitting there on the surface, and they're definitely in the sediment as well. And we've got a bivalve over to the left. And that looks like one of the swimmers. Got some swimming bivalves around here. So pretty similar to what we saw the other day, just fewer of them.
I think that word will be the one that we can.
Oh, yep. Let's see, we've also got a fish here. It's a lot of diverse in southern Chile, and there's quite a diversity of fish around here, in addition to all the other things we've been talking about.
That's where we landed, where there's nothing really visible on the seafloor, just that big fat worm.
Yeah.
Yeah, the other place didn't have anything hard
this
for
does
these.
look quite different, doesn't it?
Yeah. So the point here is, the biology is reflecting the sedimentary environment. So if you don't have a hard surface for these sessile, stationary organisms to attach to and sit on, you're not going to have as high diversity. You're going to have more infaunal, so organisms living in the sediment, like the worms we saw at the other site. So here, I'm actually seeing a lot of sponges as well in a different view. You can see actually snap that, put that in our event log. I'm going to send this to some of my colleagues who study fishes from Chile. Again, they're quite diverse. I don't know much about them, but they're quite diverse here.
Right.
Yeah. And then we can also see some sponges, some corals, bivalves, sea stars. Wow. Wow.
Okay.
Abundant and diverse.
Which is that like backscatter? They will be. Yeah. But they could just be a thing.
Ooh.
Okay.
Anemones.
So, Becky, what do you think? Oh, that's nice. So Scott said there looked to be more of a sort of feature 15 meters ahead. So I think we should go as far as that at least.
Yeah.
Just to see that,
And then start moving north.
And back.
Yeah.
Back again. Yeah.
There and back again.
So sorry. Yeah, north, then east. So
Yep.
just do a square. Sort of
Come back.
Yeah.
Yep.
And I probably want to go east quite a long way because we'd like to make sure we've
Yeah,
crossed,
go over that
crossed
picture.
that feature. Yeah.
Are we sure we want to do this flyover where we look at it, or do we want to do a slightly higher flyover where we map it with
And
the
then
multi-beam?
Just pop down.
Yeah, I think
Because
that
we were
might
struggling to
tell
see
us
a lot,
more.
weren't we? Yeah. So let's go to the feature and look at it,
Mm-hmm.
and then up, and map across.
Are you guys okay with that?
Is that okay?
To turn on the M3, fly at about 30 meters above the water, above the seafloor.
But first, could we just
Go north.
so
Yeah.
just before we start discussing something about 15 minutes ahead, we're traveling.
Right now we're facing southwest. So we're continuing southwest.
We were traveling. No.
We were traveling due west.
Okay, so this
We
is
wanted to
the
go-
track line right here. You want to
Yes.
continue along this.
Yes.
Just for 15 minutes or so, and then come. It's a nice little stuff.
Mm-hmm. Send this. What is it? Rockfish? Hmm. I have a book of fishes.
Shorefishes.
Mm-hmm. Okay, I sent it to my fish biologist friend, who's also at the Alabama Museum of Natural History, John Friel. Mainly works on freshwater fish, but probably knows somebody who knows that fish.
Yeah, come in to about 65.
Shout out.
Yellow eye rockfish.
Fortunately, the crab was not quite zoomed in enough before it left the screen to get an ID on that crab.
Widespread.
Okay, so we're just flying westward on our track. And then gonna turn north fairly soon. And we'll do a high resolution, very high resolution, the highest resolution map that we have gathered on this expedition. We're actually going to map from the ROV. It has its own acoustic imaging device on the ROV Sebastian. So we'll fly a little bit above the seabed. You won't be able to see much, but when it comes back on deck, we'll be able to see a lot. There's another feature. I don't know what that is. Could you tell what that was, Gianluca? Couldn't see what it was.
Maybe this is what's here.
There we go. That's a pretty big boulder.
That's quite big, that one. Maybe that's
I mean,
what's,
looks like glacial to me.
So there were a lot of current pushing us forward, so it's going to be when it's coming down, we're looking at it.
We are contesting with the currents here. The current direction is from the north.
It
Right.
feels to me when I was flying, just that it was coming from the east.
From the east, okay.
It's pushing me forward.
Okay. Wow. Lots and lots of krill here. Isn't that interesting how every time we kick up sediment, the krill come? Wherever they are. Yeah. Can't be too far. Frenzy going on.
Yep. I don't care. Sure. Do we want to look at that rock?
I don't think
Feel
we'll
we're
learn
gonna
too
struggle
much.
to-
We just got an idea of how large it
I
is,
think
right?
it's just a bigger version of what we looked at.
Yeah.
So, yeah, Becky, I'm happy if you were to
Okay.
come up and do that northward mapping transfer.
Okay. Let's go north.
All right, at 30 meters above.
Yes, at 30 meters above.
All right. Position.
And we'll turn on the M3. Or has it been on the whole time?
It's
Okay.
on.
It's off.
Okay.
Message on because
Alright.
Okay. He's the one. Okay.
Can we turn the Ethernet count on?
Yeah, I just want to wait
Alright.
for the reply from here. There's
Alright.
something on the software side.
So the M3 is on and the Ethernet is on. So we'll keep it at about 60, 65.
Okay, so you don't see much on here. But it's because we're picking up a little bit. We're going to be turning northward, and yep, we're almost there. Gonna just start mapping across one of the features that we saw on the sea bottom from the ship, from the acoustic mapping that we've been doing from the ship. So the seafloor surface is quite interesting here. We see some linear features that may be glacial in origin, but we're not entirely certain. In geology, we look at something called cross-cutting relationships. Means, something has to exist before you can cut it, cross over it, right? So we use the relationships of different features, like these linear features, where we have actually, in this case, one linear feature cutting over another linear feature, and they're almost perpendicular to one another. We're trying to figure out what exactly they are by getting this high-resolution map of the seafloor from the ROV to add a little bit more granularity to the larger map.
Alright, so we're 30 meters up, Steve.
So it'll look a little bit boring here for a little bit, but we're going to get some great data.
Yeah.
What time is it?
We're coming outside. No, we're just 30 meters.
We're making a map.
Oh, and then after that?
We're going on a sightseeing tour of the bottom. Yes.
Johnson just 20 meters would be better for that.
Okay, 20 meters, fine. Whatever's best for the mapping.
Yeah, it's gonna be.
I just don't want to miss
Because we're so front loaded.
Because I
with
missed
all
the
the
ship.
equipment.
Okay.
It's gonna be pretty bad, but
Okay.
hopefully I just have to go set a couple more things. Sorry. We can, but there's the vehicle's not really set up for it at the moment.
Okay.
But we can do it at 10 12. We just go through some things.
So in that case, I mean, it's tough to know, isn't it? We could attempt to just visually examine this, but it's going to be a little bit hard to hit, I think.
Okay.
And it's quite a long distance to come north and then all the way back.
It's
going to
be
hard to
yeah.
judge. It's hard to judge
Then
when we're on it.
I think we should just. We should get back into this sort of low backscatter region and confirm that that's also
Confirm that
clay.
it's also,
So then we have a few
confirm that
data
it's also
points.
sort of got those pebbles and things.
Yep.
Yeah.
Clay with a few pebbles.
Yeah. Okay. Makes sense. Yeah. Confirm both
Um,
sides. That's
yeah.
That it's got this muddier
Yeah.
linear feature.
So we'll move a bit and then we'll set back down. When we do so, do you want to fill up the 6 push core?
Yeah.
Okay.
If you think we can get anything in here.
Mm-hmm.
What's a little bit hard to judge is how far to move. Because if we would landed there and came 200 meters, we're kind of on the line.
Mm-hmm.
So to get right across this and be confident you're right across it, you're talking like 400 meters, I think.
Yeah, maybe we don't need to come all the way across it. Maybe we can
How
stop
about we
and go
go
back.
north,
Yeah.
northeast rather than north?
Okay. Yep.
Yeah.
Let's-
And then that's more efficient, isn't it?
Yeah. So we won't do quite
So
a
due-
box.
due
We'll do more of a.
northeast.
Yeah.
And then we'd be also near that. So
More of a
still-
triangle.
It's still like 300 meters northeast, though, I would say,
Mhm.
if that's the box.
Okay. Looks like we're getting a multi-beam on and moving, but is it okay?
Yeah, we're locked.
All right.
Well, okay.
We
Well,
were
let's just-
thinking of changing our heading
Okay.
to northeast instead of due north. Because there's this linear structure that we really want to go over, and we might actually save some time to do it this way and then come back this way,
Okay. Yeah.
perpendicular to the feature.
Okay. Should we just go to both 300 meters and 300 meters?
Yeah. Yeah. So we'll make a
northeast and
triangle.
Northeast and southeast.
Yeah.
Alright, so 300 meters to the northeast and then do 90-degree turn to
Yes,
southeast.
exactly, exactly.
Alright.
Super. I have to do outreach at 1:45, so I think I still have some time.
Rodrigo wants to meet. Thinks we need to.
He wants to meet.
Yeah, we need to meet for lunch. Yeah. What time's your outreach?
Okay. At 1:45.
Okay, maybe we can have a quick chat.
Okay. It's too bad. Maybe she can help orders.
Yeah, no, I get it.
I think
Yeah, it's
it's
difficult to know.
Yeah.
Let's
Just,
discuss.
yeah, we'll discuss
Yeah.
later.
So we are 20 minutes away. Okay.
Sorry, stay by one. That's just gonna have to reset the items here.
No worries.
Alright, you're good to go.
Alright, so that's 300
Yeah, that's good.
meters from. I have no positioning now.
It's beautiful, isn't it? This is just beautiful to me, watching them swim around. Yeah, we're making those little fish happy.
You trust that it's pretty solid.
Yeah, I'm hoping we see some of the critters that eat the krill. That would be cool.
Good.
I think this would make a good screensaver.
Navigational straight analysis as we get the clear start.
Okay. So we're at about 115, that's 115 meters water depth. We're about 20 meters off the seafloor. We're creating a map of the seafloor at very high resolution with a device that's on the bottom of this ROV. So we can acoustically sound, send little pings down to the seafloor right in front of the ROV. They come back to the ROV to a receiver. And based upon how quickly that ping comes back, you can tell how far away that seafloor surface is. And from that information, from lots of little dots that come back from those pings, we then can create a map of the seafloor. And it's really amazing. Some of the coolest maps I have ever seen are those collected from devices like this, from remotely operated vehicles going close to the seafloor. And you can't really see what the map looks like, actually. You can't see all those little pings in the surface of the seafloor until it comes back. Clean it up. But then we have a really nice high resolution, very detailed view of what the seafloor looks like. There's some smaller features that we're interested in here that could give us some indication of how the sediments arrived here and how they might be arranged based upon movement of the water over the surface or past movement of ice, a solid, over this area. 20,000 years ago, we had a kilometer thick ice sheet here in southern Chile, Argentina, and this was a Patagonian ice sheet. We would be in the area of the northern Patagonian ice sheet right now. And so we might see features that were left behind by that ice as it was grounded on the seafloor here. 130 meters water depth. It's actually not too deep for marine geology standards. Actually having ice fill this basin, and then as it melted and retreated back to land, it leaves behind features as well. So we'll be able to see those with the high resolution maps that we're creating right now. But for the meantime, enjoy the krill view. Yeah, so somebody's put in the comment, if a giant whale comes through to eat those krill, that would be a cool screensaver. Yeah, some of the largest creatures on Earth swim in these waters, blue whales. It'd be really cool to see one, but I hope that we don't, because we want Sebastian to have a nice, safe journey back to the Falcor and do a map and bring him back up. Yeah, Yeah, so the krill like to eat plankton, copepods, which eat the tiny phytoplankton that I like to study, things like diatoms.
ROV bridge, are you happy with 0.4 of speed?
All part of a very
So we'll start at 0.3.
complex, interesting food chain here in the ocean.
Understood, 0.3.
Becky, we're doing this at 20 meters above seafloor.
Yes.
Yeah.
Yeah, it didn't do well at 30.
Didn't do well at 30.
Just keep moving that. You can move that waypoint.
Yeah, fine.
But-
Let's take it.
That's
fine.
All right, so I'm going to pass the controls back to our fearless leader, Dr. Seb Watt from Birmingham in the UK, who is the lead on this project and our chief scientist. Take it away.
Thanks, Becky, and thanks for covering this dive. Becky's just got to head off to start planning for one of the ship to shores we've been doing on this project, and we've been doing a lot of ship to shores, which is really exciting. Big part of our plan is to sort of maximize the outreach activities that we're doing during this project. You've made a lot of connections with local schools in particular. So in the Chai-ten region, there's a fairly small number of schools, a lot of which are in isolated island communities. So as we've been coming down here towards Chai-ten, we've been passing several small islands. These are in the sort of inland sea between the Isla Chiloé, which is this big island off the coast of Chile, and the mainland coastline. And there's lots of communities living on these islands. The teacher we have on board, who is leading a lot of these ship-to-shore activities, the school has a very small number of children. And I think it's the same with several of the schools that we've been connecting with on these surrounding islands. So it's an interesting region, and it's very sparsely populated really overall, and the town of Chai-ten is therefore a significant local town. It's sort of a regional hub for quite a large area. And this is the town that was devastated in the 2008 volcanic eruptions. The entire town was evacuated. It is now rebuilt, and sort of the population is living there again. But this has had major changes, as you might imagine, on this town. And for a long time after the eruption, there was a lot of uncertainty over what the next steps would be. So it took some time for the town to be reconstructed and for life to return, in the sense of a population coming back to this town. And the town of Chai-ten is only accessible via a series of sort of ferry routes and road routes. There's no road from northern Chile directly to Chai-ten. There are ferries from a little way south of Puerto Montt that sort of hop between various locations. There's several sort of pretty isolated coastal villages. There's these island communities, and Chai-ten, although it's not a large town, is the sort of significant settlement in quite a big area of this part of Chile. There is a road south of Chai-ten, and when you drive south of Chai-ten, that continues that road for all the way down to the city of Coincide, which is several hundred kilometers south of here. So, yeah, really remote part of Chile. So really exciting to sort of be able to connect with the school communities in this region. So we're getting towards the, 2020. Okay. So we're coming towards the later part of this dive, and the video feed is, blue water, as you can see, with this sort of suspended organic matter. And the reason we're doing this is we're sort of 20 meters above the seafloor, and we're trying to maintain that altitude, and we're trying to maintain a consistent direction to the northeast. And then we're going to go 300 meters in this direction, and then we're going to turn to the southeast and go for another 300 meters. So I'm afraid the sort of video feed will not look the most exciting, but this is collecting important data.
ROV bridge, do you want me to move to that new position?
Yes, continue follow it.
Yes, just continue following our way.
Understood,
Yeah,
understood.
you can speed it up to another 0.1.
And you can speed up also 0.1. Another 0.1. So let's
300 meters to the green waypoint, and then 300 meters to the southeast. Is that okay? So, dog leg. So 90 degrees, John. 300 and 300. Like that. Yeah. Sorry, just discussing the plan for this transect. So the idea of hovering 20 meters above the seafloor and doing this slow move in a consistent direction is that we essentially get a strip of mapping data of the seabed at very high resolution, because we're just 20 meters above the seabed. So this will be quite a narrow strip of mapping. Essentially, the deeper the water, the wider the width of your mapped profile, but the lower the horizontal resolution, so the sort of less detailed that image that you get. So we can use this ROV to hold it a short distance above the seabed and get a very high resolution map. And we're particularly interested in that right here at this dive site, because the seabed is marked by these enigmatic features, which have distinct properties to the adjacent features. They follow sort of streaked patterns, although some are a bit more sinuous and wavy. And we've been discussing the origins of this since we first mapped them yesterday. We think they may be glacial features, and we'd like to get confirmation of that, or get additional evidence, if you like, to support our interpretation or test our interpretation. So that's what we're trying to do with this mapping. So we're just holding still at the minute, actually, and then just some discussion around the plan, and then hopefully we'll move across. So I still see I've got several of you on the feed who've been here, I think, for most of the dive. So thanks all for tuning into this. And it's great to see several of you who I've also noticed are on the previous dives as well. So it's quite a few of you getting quite a lot of insights into what we're doing on this expedition. The ROV dives, of course, are just part of it. Yesterday we spent the full day collecting geophysical data, hydroacoustic data. So by that I mean seabed mapping, looking at the bathymetry, the shape of the seafloor, but also the backscatter properties. So the sort of surface acoustic properties of the seafloor, which is informative for us about the nature of the seabed. Is it covered in softer sediment, coarser sediment, hard rock, and so on? This is actually how we spotted these features that we thought may be glacial. And we're also, really quite importantly for this project, collecting sub-bottom profiles, which is like a sort of shallow picture of the layering beneath the seabed. So it's penetration down to, in well-layered sediment, penetration down to a few tens of meters, and we can see the relationships between those layers. We can identify something about the form of those layers, cross-cutting relationships in those layers, how they may get thicker or thinner, where those layers are accumulating and where they're not accumulating, so where there is erosion rather than deposition. So this is really helpful both for planning our coring sites and potential targets for sampling.
Yes, that is correct, and we change it right away.
Understood.
So sorry, just a short interruption there. To the feed, there's just some discussion going on the plans for this transect. So sorry, where was I? Yes, sub-bottom profiles. That's what I was talking about. So this is important to select our coring sites. Obviously these ROV dives have to be carefully selected. We're covering a huge area here. We're mapping hundreds of kilometers of distance during the course of this expedition, and we can only pinpoint a few sites with the ROV. So we really want to choose those to get representative coverage, to test ideas, and to really select what we think will be the most informative points. And we're certainly learning new things on every ROV dive, and this is helping inform the strategy going forward. So those sub-bottom profiles are really valuable, and we're recovering some amazing seafloor imagery actually on this project. So the ROV dives are just part of the picture of the full data set that we're getting. We've also been doing a lot of CTD profiles, which we use information to understand currents, salinity, mixing of water bodies, and we've actually been doing more of those than I was initially expecting on this project, but it's also proving a novel data set and really informative as well. So we have a student from the Universidad de Valparaiso who is leading that, and a colleague from NOAA as well on the expedition, working on that with her during her time here. So that's it's great to have such a broad team all working together, and indeed, the wider team across the whole ship, supporting this expedition. It's been really exciting to work with such a range of people. Okay, so are we moving forward, Chris?
Oh, yeah.
Just waiting for...
No,
Yeah,
we're going.
Yeah, cool. Sorry, it's
Right
just hard
there,
to judge.
that's our speed over ground.
That's
the
0.2.
speed over, yep.
Yeah, okay.
So we're heading here, we start down here.
Yeah, cool. Okay, and we're acquiring the mapping data. Yeah.
Fellas,
Cool.
we're not in any sort of hurry today, but I'm just checking if you had a timeline. So I'm ready. We're next time. What are you thinking? 30 more minutes?
So 500 meters essentially to cover at this speed. So what's
Okay, so a while.
500
Yeah,
meters?
so the plan's that, we're gonna go here to the apartment,
Okay.
and then we're gonna go 90 degrees southeast, another 300 meters. 1.2. So it's a strong side current, so we're gonna be faster than the other direction.
Everything's been pretty good.
There was a glitch with INS positioning, so we switched to USBL, which has been very solid.
Okay.
Other than that, yeah.
So that would be 40 minutes at this speed.
Wonder what happened to that? Where's John?
Huh?
Oh, that ADCP went out?
No,
Yeah. Seb, there's a really good question on Twitch. Did you already answer it or no? I was just
Oh,
checking
this one on the
my
left?
key. Yeah, on the right.
On the right,
Yeah.
indeed.
The other left.
The other left, thanks, Sophia. No, I didn't answer that because for some bizarre reason, in my head, I'm only seeing those two chat feeds.
That's
I think
okay.
it's because the other one's shorter. I hadn't noticed
I've also zoomed it in, so it's easier to
So,
read.
yeah, I can see that now. How much damage did the Lahars from the Triton eruption do to the seafloor, and how has the region recovered since then? Okay, so I think in a nutshell, that is a key question that we want to answer on this expedition, and that is really an unknown at the moment. So the Triton Lahars came down two river valleys, one to the north of Triton called the Rayas River, and the Rayas River is also fed from other nearby hill slopes, including those draining a volcano called Minchimahuida. And then to the south of Triton, there's quite a short river system, fairly small drainage basin, which includes the lava dome of Triton and the southern slopes of Triton. And that river system, which is called the Blanco River, was received a lot of sediment, huge volume of sediment directly from the Chai-10 eruption. So the lahars down that Blanco River came directly down that system without that much modification in terms of picking up other material and inundated Chai-10 town. The Rayas lahars are less voluminous and probably a little bit more mixed in terms of the pathway they followed and the amount of erosion along there. So in Chai-10 town itself, so I've seen these deposits. I saw these in, a little while after the eruption, but in the town, and for the most part, if you can picture the sort of coarseness. So a range of sand grains from sort of fine to quite coarse sand, but they're not full of big rocks and dense blocks. They were very rich in essentially that material that was directly erupted by the volcano. So this is inflated pumice clasts and fragments of those clasts, so down to what we call volcanic ash grade. So that's sort of sand-sized and below fragments of volcanic material, but still quite like low density, a lot of that, because it's quite bubbly in the larger grains, and even the finer fragments are not a particularly dense volcanic rock type. So the material coming into Chai-10 town was dominated by this pretty fine, generally sand-sized material with some larger pumice blocks, so pale-coloured pumice, and a few other fragments of other materials. Now the lahar that entered Chai-10 was, in the scheme of lahars, relatively dilute. And this meant that when it overflowed the riverbanks, it spread widely, and as the water drained away from that, it left behind layers of this volcanic sediment, fairly pale coloured, sort of palish grey, and setting hard, a bit like a sort of a concrete type texture, if you can imagine that. And this flooded across the town and left this hard layer that was a metre and a half in thickness across a lot of the town. And this was fluid enough, this material, that it sort of spread through areas with housing and so on. So it really sort of was highly destructive and sort of infilled the topography, forming this sort of really flat surface where this fluidized material had spread through the town. Now the town had been fully evacuated by this point, but if you can picture what I've just been describing, this is clearly enormous volumes of material, way more than could be tidied up or cleared up through sort of excavation. So this sort of caused huge amounts of destruction. And it was a long time before the town was reconstructed, particularly in those damaged areas, and repopulated. Now, what that material also did when it hit the shoreline is it was deposited on the shallow seafloor, and it built up to an extent that that former marine area became above sea level. So it built out a delta with this sort of sheet-like deposits of volcanic material. So low gradient, very flat deposits that extended way beyond what was the former shoreline. So in Chai-10 there's a road that was along the shore with a sort of grassy bank, and that was the seafront. After the eruption, you'd be stood on that road and you'd be looking out over, in places, kilometre and a half of what sort of looked like a sandy delta plain, with a lot of debris sort of that had been transported and then deposited, really transformed. Chai-10 town, the former harbour, could no longer be used because it was sort of inundated by this material. So it took a while for a sort of new port to be established in a slightly different area just to the north. And still today, that coastline is sort of permanently shifted. Indeed, some of this new land, is becoming vegetated. It's quite interesting to see how it's evolved through time over the last 16 years or so. Now, obviously that delta that has extended the coastline will have a submarine equivalent, and this is what hasn't been studied before. So there's really no clear information, there's been no detailed surveying beyond the very shallowest delta front. There's been no surveying to really understand the impacts of this eruption. How far do those deposits extend offshore? How did they flow when they entered the marine environment? How far did that sediment get carried and dispersed? What is the sort of footprint of the Chai-10 eruption in the marine environment? So these are all questions we're trying to answer here through this combination of approaches. And right now we really don't know. We don't have that information. So we'd like to understand the thickness of these deposits, their spatial dispersal, the processes that disperse them, how they evolved perhaps through that transportation process, and indeed what the impacts of these sort of potentially catastrophic perturbations in the environment, what the impacts of those are on the existing life and indeed the response and recovery of that system. Potentially events like this can, although they might cause burial, they also introduce new materials, new rock types, even new nutrients potentially. Earlier in this dive we were seeing some rocky substrates on the seabed which were colonized. Large mass transport events of this type can, for example, carry in rocky material into an environment that wouldn't otherwise have rocky material, it would only be accumulating mud. So they could even introduce new environments that sort of sustain new life. So it's not a matter of destructive change, but a change nevertheless introduced by sort of new environments that can be established by the inundation of these new materials, particularly new grain sizes. If you introduce pebbles, cobbles, that is going to sustain a very different assemblage of life than a muddy seafloor. So all sorts of interesting changes could occur around these sorts of events, and that's what we're exploring here. We're already getting some new understanding from what we've seen so far. We're certainly learning a lot about sediment transport patterns in the region, linked to our observations of bed forms and currents. Where we've been looking in this dive actually seems to be an area with very limited deposition, so it may be that some of the sediment is bypassing this region. But quite near here we're seeing seafloor that is quite different in character, and where there seems to be more deposition, and that's something we'd like to examine potentially on the next ROV dive. So as we're collecting this mapping data each night and some of the daytime, that is informing our understanding of the characteristics of the seafloor and where we choose these next dive sites.
Go ahead.
So it's a great question, and one that I hope we'll be able to answer more clearly in the next couple of weeks, and even more clearly when we've worked on these samples after this expedition.
Please come back to point 3.
Understood. Point 3.
Okay, so yeah, happy to. Yeah, I mean the marker's not too critical. I think we've done the distance. I'm happy to come through it and then southwest.
Okay.
Whatever's easier.
Yeah.
Oh, sorry. No, I was seeing the yellow. The green's the way. Sorry. Yes. No, we do want to. Yeah. We do want to continue up to there, and then I was seeing the yellow.
Yeah, this is for the ship. So
Yeah.
we'll get to right here
And then southeast. Sorry. Yes.
What's your pitch?
which is negative 15.
So I got another good question in the chat actually about pumice rafts. Yeah, that is a good question. So pumice is a low density rock, and it's low density because it's full of space. It's full of what we call vesicles, but you can think of that as bubbles in the magma. So when magma is under pressure beneath the Earth's surface, as with any liquid, there is a relationship between the solubility of volatile species. By that I mean things like water, carbon dioxide, halogens like chlorine, fluorine. So elements that at low pressure or that at low pressure would be in the gas phase, so what we call volatiles. So magmas have dissolved volatiles in them. They carry dissolved water. It's the most abundant volatile. They'll carry sulfur, either in the form of hydrogen sulfide or sulfur dioxide, carbon dioxide, halogens, and so on. So magma can have a mix of volatiles dissolved within it. Now, at higher pressures, the solubility of those volatiles increases, which basically means that magma can hold more volatile elements within it at high pressure when it's well beneath the Earth's surface, sort of several kilometers depth or more. Now, as that magma ascends towards the surface, the pressure reduces on that magma, and therefore the solubility of those volatiles decreases. And this means that essentially during ascent, if you exceed the solubility of those volatiles, they go into a gas phase. So you start to form bubbles in your magma. As the magma continues to ascend to the surface, the solubility decreases more and more, and the magma can hold less and less dissolved volatile material, and so you get more and more bubbles forming. It's the same concept as a pressurized bottle of drink. So if you get a fizzy drink, that bottle is hard, it's under pressure. When you open that cap, you're reducing that to atmospheric pressure, and the bubbles come out of solution. At lower pressure, the solubility is reduced, so those bubbles will come out of solution. They'll exsolve. They'll no longer be dissolved in the liquid. The exsolution of volatiles is exactly what happens when a magma comes up towards the surface and the pressure is reducing. And this causes huge changes in the physical properties of the magma, huge changes in its viscosity. So how sort of fluid it is, in its density, because you get enormous expansion with the formation of gas bubbles, and this can cause acceleration as well. So this is really fundamental to the behavior of magma as it ascends towards the surface. With sufficient amount of gas in that magma, sufficient volatiles, the bubbles will eventually connect, and that causes fragmentation of the magma, and you get a transition from a bubbly liquid, like a foam, through to a fluidized mixture of gas and fragments of magma. So the magma is literally fragmenting through bubble expansion, and this is what occurs in an explosive volcanic class as like a volcanic foam, if you like a quenched volcanic foam, and the finer fragments of ash, particularly the very fine fragments of ash, they are literally the sort of the bubble walls, the surrounding, the material as these bubbles were expanding and eventually fragmenting that magma with ongoing expansion. So in explosive eruptions, particularly in high viscosity magma, this very efficiently produces huge volumes of very fine particles with very high explosive energy from that bubble expansion as that magma is accelerating towards the surface. And if you get fragmentation before you reach the surface, then that is the condition for explosive eruption in this style. So that is essentially how the Chai-10 eruption worked in its early phases. It was explosive. Now actually later, the magma had lost a lot of its gas, and so the later magma that was ascending was actually very volatile poor. The gas had been lost, so it came out as a very, very viscous lava. So the key to that transition between lava producing and explosive behavior is linked to that volatile content. Now, that was a long-winded way of getting to this question about pumice drafts, which is sort of why pumice is low density. So as I say, you can think of it as like a magmatic foam that is solidified. It's a solid. But when you look at pumice, if you look at pumice under a highly magnifying microscope, electron microscope or something, you would see it is absolutely packed with bubbles, with very fine walls between those bubbles. So the majority of it is space, and in between those bubbles we have these thin walls of a material we call volcanic glass. So when you cool that magma either rapidly or when its chemistry prevents crystallization, then you get volcanic glass. So pumice is this low density rock full of bubbles, of pore space on a very fine scale often. So often those bubbles will be too small to see with the naked eye, far too small. And this makes something that can float. So after large volcanic eruptions, either ones that occurred subaerially, like the Krakatau eruption in Indonesia in 1883, or indeed after submarine eruptions, so this has been observed in several cases quite in the last few years, Submarine eruptions, so both these eruptions can produce pumice. So if you have an island eruption like at Krakatoa, or a submarine pumice producing explosive eruption, then that pumice will float. It will be on the sea surface after these events. After the Krakatoa eruption, for example, that pumice raft clogged up much of the Sunda Strait between Java and Sumatra in Indonesia, and those rafts of pumice were observed for months right across the Indian Ocean, carrying debris on these rafts. They were observed on the shorelines of Eastern Africa, and I think rafted pumice has been observed after the Southern Atlantic. I would have to check that, but I know there's a lot of reports down the African coastline of pumice rafts lasting for months. So this is, obviously an interesting process after a large volcanic eruption. But these pumice rafts, again, create sort of quite a unique environment, and they can retain their form and be dispersed by currents and strung out. And as I said, it can also carry material literally rafted on these sort of large fields of floating pumice. Now, after Chai 10, I was not aware of reports of floating pumice, actually, until I chatted to a colleague right at the start of this expedition, a colleague who I met in Chile just before getting on the ship, who is based in Puerto Montt and works in this region. And just from our conversation, he was saying how on the shores of Chiloé he observed pumice, floating pumice. So that's an indicator of likely pumice derived from the Chai 10 eruption, which entirely makes sense. The Chai 10 pumice was very low density. We know these lahars carried material down to the sea. So although I haven't seen sort of specific reports of it, it sounds from that conversation there certainly was floating pumice, and that some of that was dispersed across this inland sea, across to the shores of Chiloé, which in this area is a few tens of kilometres to the west of where we are right now. In terms of what we've seen so far, we did actually recover a couple of dives ago on the seabed a piece of pumice, probably about 20 centimetres across, on one of the ROV dives. So most of the pumice we've been finding on the seabed has been pretty small, up to a sort of size of a small pebble. But we did see a sort of larger block of pumice that we picked up on one of the ROV dives. And I've certainly seen pumice blocks of that type in the Chai 10 deposits on land. And it was waterlogged when we picked it up. It sort of was quite heavy, but before this pumice gets waterlogged, it can float for quite some distance. So we're just turning the ROV. I'm not quite sure if you just see the video feed or if you also get a sort of map feed. But the ROV's just turned, and we're about to start on a transect, still 20 metres above the seafloor, but now travelling to the southwest, so perpendicular to the last line. And this is, again, to cut across one of these seafloor features that we've been exploring on this dive. So we're now coming towards the end of this particular ROV dive. We're just going to take a 300-metre line down to the southeast. And we can't see anything visually right now because the focus of these transects 20 metres above the seafloor is to collect mapping data beneath the ROV. So high resolution mapping data.
I started a new line right before you guys got going. So
ROV bridge just to confirm one thing. The heading that I had currently, you are happy with it?
Yeah, the heading works great for us as long as it's easy for you to maintain your position with that.
Yeah, that's good.
All right.
Right, so just starting on that transect now, the final transect of this dive. We're into that, travelling at 0.2, so I guess about 15 minutes or so before we finish this transect, and then we'll be coming back up onto the ship, and we'll get to see the samples that we collected earlier. So for those who were on at the start of the dive, we started off on a pretty muddy seafloor, collected some scoop bags, which are used by our biologists. Is that behind me? Biologists from the Universidad de Valparaiso in Chile. They're particularly interested in the small-scale fauna, what they call the Maya fauna. So, how big are the Maya fauna, Gianluca? Like millimeter scale? No, sub-millimeter?
Yeah.
Sub-millimeter. So sub-millimeter scale organisms. So not things that we're likely to be able to see on the dive, but that they sieve the sediment for and look for afterwards in their samples. But we did see some larger fauna there. We saw a worm at the start in this muddy sediment, and then we moved across. Well, first of all, we took some cores in that muddy sediment, and one of those seems to be quite successful. But what we were finding is that beneath that soft, muddy seabed, perhaps about 30 centimetres down, we hit a much harder surface, and that's the surface that I think is broadly characterising the seabed in this area. We're interested to know what that is. So we got one core into that. The other cores were struggling to get into that. And then we moved across away from the primary feature we were examining. And actually, as we expected, the characteristics of the seafloor changed and became much harder when we moved out away from this muddy sort of linear feature. So that harder seafloor, we could see much more, I mean, I'm hesitant to say more diversity because we haven't sort of looked at the biology, but I guess more variety of seafloor dwelling organisms was certainly visible. So we were seeing corals, brittle stars, echinoids, anemones, some fish, a whole variety of, and a more colourful picture for those who were here. And that's because of the change to a rockier substrate. So we're seeing pebbles there, some larger rocks on the seabed as well that were being colonised by these organisms.
Yeah, you keep that position relative to us all the way down to the.
And then since then, we've lifted up and we're essentially collecting a map then across this transition. We want to understand the nature of that transition between the muddier seabed and the stonier seabed, and to understand the structural relationships between those. And this will help us ultimately arrive at an interpretation of what's formed these.
Yeah, that she's busy in 1:45, I think.
Okay.
So you think you have some time between now and 1:45? So what I want to do is very short, like so to present the problem. And so we don't have to come up with solutions right now. We can think it over, but at least get it in our brains, and we all can do it. Sure. So it will be like 20 minutes.
Now let's do it.
Okay, but
Unless we can get someone else to finish off here.
yeah, because we both really need to take a nap.
Take it.
Yeah, I slept 3 hours.
Do you want to ask Alex to take over? He was doing it earlier. So Chris, yeah, the plan is to finish this translate.
Okay, so you want to do that 6 push bar?
The time we've got there, it's going to be quite hard to pinpoint exactly where we are on this backscatter. And we, it is that heavy season. I'm sure we're going to get them.
Look at the regular one?
Yeah. Okay.
I mean, it's up to you. It's worth giving it a shot.
Well,
Give it a shot.
we're
It's
not
not-
back there, are we? So 20 meters. That won't have a lot of. We wouldn't have a lot of time to do that. No, I think it's a good idea. Yeah, why not? So, alright. So at the end of transects, why not just land the one push call, and then call it, as we build the rest of the sample.
Okay, we're just changing over people. So yeah, for those I was on earlier a bit today, but yeah, I'm Alistair Hodgetts. I'm a researcher at the University of Edinburgh in the UK. I'm English, not Scottish, which is why you've got the nice soothing English accent here. Say that around all the Americans. I've got very varied accents to me, but so yeah, we're just transiting at the moment. And we'll see what interesting things we can see on the way. Have you seen any interesting things recently? There's a lot of nutrients in the water. Oh yeah, I did see this. So we've had a lot of krill knocking around. So yeah, so my research background, I'm a volcanologist. So I started off working on effusive eruptions, which mostly produce lava flows, and looking at the interaction between lavas and ice, so subglacial eruptions. And then I've sort of moved into more explosive volcanism. So my PhD was looking at really explosive eruptions from Mexico. I was working around the Mexico City region, so very similar to here actually. I was working on cores which were collected from a lake in Mexico City. The whole of Mexico City is built on lake sediments, and after the Spanish conquest, all of the lakes were drained, so it's just a big open vast lake bed. There's a few smaller lakes which exist, so we took a core from one of those lakes on the southeast edge of Mexico City. Mexico City is kind of surrounded by a bowl of volcanoes. There's tons of volcanoes just like there are here in Chile, but around Mexico City particularly, there's a chain to the east which has got three major, what we call polygenetic volcanoes, which means that they erupt more than once. Over on the west side is another large volcano, and below Mexico City is around about 200 smaller volcanoes which we call monogenetic, meaning they erupt more than once. So this is really similar to here in Chile. Yeah, we've got all these stratovolcanoes, these polygenetic volcanoes, but we also have lots of these monogenetic smaller volcanoes which are perched on the flanks of these larger volcanoes. Or also appear in these volcanic fields as well. So the ashes that and the geological layers that we're expecting to see from these volcanoes in Chile are from both types of these volcanoes. What we've seen so far is we've seen really fine-grained white to sort of grey pale ashes, which are from these larger, more explosive eruptions. The colour kind of indicates, as it's a whiter colour, a greyer colour, indicates more silica-rich eruptions, and a darker colour would generally resemble something that has a lower silica content. It's a bit more of a sticky magma, a bit like treacle or honey sort of consistency, and that rather than having lots of gas which can readily escape out of that, we end up producing a lot more lava flows from eruptions like that. So my PhD was looking at these lake cores, and I mean here we're recovering the upper metre or so at the moment, maximum really, whereas these cores that I'd collected were down to 500 metres depth, so that was all done by drilling, and within that we found the upper 300 metres were all these lake sediments, and then below that we had loads of really coarse material, really large blocks really of which we interpreted to be lahar deposits, and at the base of that some lava flows. And within that lacustrine sequence we had loads and loads of ash layers, around about 450 ash layers. So we're applying the same, particularly from the volcanic side of things. There was also a paleo-environmental element to that project. Lots of people working across the globe, from Mexico, from America, from the UK, Germany, New Zealand, etc. And yeah, lots of people working together to kind of achieve the most out of those cores. So that's essentially what we're doing here with these cores as well. We've got a whole large team really of brilliant scientists. Over half of us are from Chile and know the volcanoes and the environment better than anybody. And we've got specialists all over. We're still transiting at the moment, keeping our eyes peeled for any interest in life. So personally, it's my first time in Chile. We didn't have long here before we boarded the ship, but it's an amazing country. Managed to climb up one volcano just before we got here, up Osorno volcano. We set off from Puerto Veras.
Can you spend some time in the country? Can you spend some time in the country when you cruise?
So I've just got a few days, but then I'm heading back basically. So I've got to get back for all that, which is unfortunate. Yeah. Have you spent longer? Yeah.
Third trip to Chile this year, so I did Atacama Desert. Santiago this time, so I'm going to go to
Incredible. Yeah. I've got a lot more of South America to explore. Yeah.
Alistair, can you tell me a little bit about what made you want to become a volcanologist?
Yeah, sure. So I guess when I was 16, in the UK we do things called A-levels, which is kind of, we call it college, and it's different to Americans, but it's where we study fewer subjects at school before we go to university. And I moved to this college, and I went to go and look at geography at open day. I'd always really enjoyed studying geography and the volcanoes and earthquakes and that at school. And as I sort of left at the open evening where I went along, there was a geology department next door, and they weren't having many visitors, so it was just kind of a few people, come have a look at this, and I sort of spoke through. I think they were talking about how it ranged from looking at dinosaurs, all the why I found the cool parts of geography anyway. And so I just took it on a whim, essentially I did that for a couple of years, and I really actually was really interested in wildlife, and I'd sort of volunteered at nature reserves and kind of had my heart set on working in conservation. And then as I sort of studied geology a lot more, I realised that actually, you've got all these, just like this, you've got opportunities to kind of follow that passion as well, but do something as well which I found really, really interesting. So I then went to university and studied geology for 3 years, and as part of that, I guess the volcano side of things was what I enjoyed the most, and sedimentology as well. A lot of volcanology is sedimentology. Anything that's explosive that comes out of a volcano, as soon as it's out and it behaves like a sediment, it's transported like a sediment in the atmosphere. It falls like a sediment, and it is a sediment even though it's an igneous rock. So I kind of enjoyed both elements of those, and ended up taking that further, and then studied for a master's degree in that, and then a PhD. So I wasn't particularly one of these children that was really fascinated by volcanoes and things. I guess growing up in the UK, we don't have many. Well, we've got some, but they're extinct and very old. And
What made you go from studying less viscous lavas and less explosive volcanoes to more explosive volcanoes? Was there a shift there?
I don't know. It's really good to be well-rounded, I guess, in terms of things. very normally in an eruption, it won't be entirely explosive or entirely effusive. You'll have, in an effusive scenario, you'll have minor elements of ash which are produced as well. Same in an explosive eruption, you will still also have lava flows. So I guess before I did my masters, I did an internship at the British Geological Survey, and that was really, really varied work. It was you can imagine a volcanology team in a country that doesn't have any volcanoes. It's quite varied. Kind of assisting other agencies across the world with different things. We have our own sort of like alert level system related to global activity, and every single day was different. And during that, I kind of became quite interested in some of the Icelandic stuff that had happened. Because we were affected in 2010 by the Eyjafjallajökull eruption in southern Iceland, where lots of fine ash was generated from meltwater and was transported across all of Europe, really, and caused massive widespread disruption to air travel because planes couldn't fly, and with the risk of ash getting into jet engines. As part of that eruption, there was lots of lava flows as well, but looking at the deeper history of that volcano, there was these layers which in the geological record look like they were lavas, but you can get these things called rheomorphic ignimbrite. So an ignimbrite is a deposit from all the pyroclastic flows, these clouds of hot dense ash and other rock material that's coming out of the volcano, and when they settle, they can sometimes retain their heat, and all that ash can kind of gel back together, and then it can start to flow like a lava. So you're looking at a secondary sort of process that's happened there, and you can't really tell if it's a primary lava flow deposit or if it's one of these rheomorphic ignimbrites, which is actually really made of ashy material, which is kind of turned into a lava after that. So I kind of wanted to study that stuff, and I was speaking to somebody at the British Geological Survey about that, and following that I went to go and do my masters, and realised that actually somebody was working on that project from talking to somebody who works in Iceland a lot. And then from that point they sort of suggested another project, which was this subglacial volcanism work, and it was mapping a volcano which had never been looked at, and trying to piece that together. And we discovered by the end of it that it was this new type of glacier volcano. But during that, I guess I was really, really interested in all sort of areas of volcanology, and I never actually particularly wanted to do a PhD. And then I was sort of, my supervisor at the time had sort of recommended to me that I looked into it and had a look at some available projects that were being advertised, and I looked at those, and then I picked about 3 or 4, I think, which I found pretty interesting, and just so happened to be that all of them were related to quite similar things, looking at explosive eruption deposits and ash and things like that. And one of the projects was this project in Mexico, which was working with Dr. Sebastian Watt, who's the chief scientist on this cruise and this expedition. And I guess from that point it's just sort of gone from there. So that's quite a long answer. Yeah, so we're closer to our site now. Just seeing lots of nutrients floating around. Biologists are going to yell out to me if they see anything on any of the other cameras. You guys see anything? Yeah. Brilliant. Just seen one of the comments about being a volcanologist in Chile must be like tripping a candy shop for kids. It certainly is, yeah. I think that's one of the most really interesting and the coolest part of the jobs, I guess. You know, it's a travel element. You know, you can be away from home for long periods of time, but yeah, you get to go to some amazing places that you wouldn't particularly visit on a holiday, really. Parts of countries that you just never see as a tourist. And I find that quite exciting. But yeah, Chile, yeah, as soon as sort of landed and even from the flight, views over the Andes and things like that, was incredible views. So see some comments as well about Azores and Villarica tephras as well, having samples. It's great people have got their own samples and their collections of these things. That's something I guess I'm trying to do less of as I go further along in my career. Is as I started, I collected loads and loads of rocks everywhere I went, and now I just try and take a small one. Otherwise, I'm not going to have any space to keep any of these things. My wife will kill me as well.
Do you have a display case for some of your findings?
Yeah, I've got a display box where we recently moved house. I say recently, it was about a year ago, but anybody who's moved house knows it takes a while to like unbox everything and get everything together. So yeah, probably will get a nice display cabinet, I think, to display some of the nice specimens in. But yeah, I've got them all kind of labelled up in things, and yeah, I have a big collection in the university as well, so that's good. Yeah. But I definitely have to get some from Chile.
Yeah. You guys will set that push forward versus the Atlantic
How's it going?
Yeah, it's good, yeah.
We still not finished the transit yet?
Not finished transit, no. Still chugging. Yeah.
Stay there.
Okay. Yeah, just about some of the other data we've been collecting. So yeah, when we're not doing these ROV dives, we're essentially mapping the seabed. We're getting high resolution bathymetry data to see what the topography is, and that's helping to inform us of where we're going to be doing these next dives.
Thank you very much. We're going to finish this transit, go down, take the push forward, and then we'll start recovering.
Cool.
Understood.
Yeah, so this mapping data really informs where we're gonna do our dives. Also potentially the types of sediments and lithologies that we might run into. And as part of this, we can also take some shallow seismic profiles as well to try and get an image of the upper portion of the sub-bottom or the strata which are below. So this can allow us to look for any basins or sediment infills or anything that's happening under the surface that we can't see just from a sort of image from top down. We construct these in lines, so our geophysics team and GIS experts yeah, they carefully work with the crew and the bridge and captain to basically plot out all these lines, and then when we need extra transects, we cross-cut these lines. So just looking on the one screen, and we've built up a really nice image of the sub-bottom here, which is absolutely brilliant.
Alright, so that's pretty much us there. Go ahead and come on down to the seabed.
So we're just approaching our next site. So hopefully the cameras will show something a bit more interesting now.
That he wants to start going up?
No, it depends on how long it takes us to do this push core, which shouldn't be more than like 5 or 10 minutes, I wouldn't think.
Leo, recovery.
M3 logging is off.
You just see approaching the seabed. That's good. Yeah.
That's the seabed. So 13.
Okay.
Nothing ominous about that at all.
Just a bit of sediment picking up as we're landing. Wait for that to settle. Okay.
This guy right here, yeah. The red.
So here comes the arm just left to the core. So it's going to be a push core we're going to take. It's a bit like a straw. You use a straw to suck up some juice or water or any chilly beverage of choice, and you kind of use that suction to keep some of that liquid in the barrel. It's kind of similar to how this works.
That looks soft up. So is this one already done, or is that just from something else?
Yeah. Can we check number 6 gets done?
This is not.
We don't have a 6 though.
So,
Which one's 6 should be empty, should it?
Yeah.
You did 1 to 5.
alright, so I don't know where that's from. I don't know what that is, but we can clean it out.
Can we
Okay.
take it out? Yeah. Okay.
So take that out.
So it's can we clean out? You sure it wasn't?
Yeah.
Wasn't it? Yeah.
I'll check the monitor as well.
That's our well said it wasn't either.
I mean, it doesn't look full enough to have been done because the
No.
others were.
Okay, so it just looks like there's been some sediment which is just picked up in the bottom of this one. It should be empty, so that's why we're just cleaning it out.
No, because we can take it.
I'm concerned though that
Previous dive was on that really stony stuff, so we can do it.
bottom should be sealed, definitely though. It's 100% sealed because it's got to the bone and it's got the bottom of the chamber. Yeah. I was looking at the push work from the top down and it looks like it's still got a lot of sediment in there, so I don't know what value it's gonna have for you.
So you're struggling to clean it.
Well, just where it looks right there, the holster where it came from.
Right, yeah.
Still, there's a bunch of sediment in there from something. Right here.
Ah.
Right in the
so
bottom.
maybe that's the issue, that it was.
That there was something that.
It's sort of filled up.
So my only thought we can do it is just the bottom where when we put it back in. Suspect. Yeah, it's going to be a combination of what's in there now and what we get right here.
Okay.
Mm-hmm.
And we might bit difficult
To gauge that.
But to seed it and then we'll take it out.
I mean, just out of interest, yeah, I mean, it'd be helpful to see how easily it goes in, because I was expecting this to be a sort of firmer seafloor on the first site, so it's good to gauge that.
Okay. So it's just pushing down. It's going into sediment pretty easily. So, yeah.
You want a little bit more? Just cover those eyes. Alright, that's good.
Yeah.
Okay.
Good recovery.
Interesting. Sample easily enough, but note that the bottom of the container is sediment, so that the bottom is compromised. If I would go on the outside.
Yeah, so for those who were watching earlier, that went in much more easily than previous attempts. So just because we've got some sediment at the bottom, we will have some contamination at the bottom. So yeah, we won't be recording that. We can only really use the upper portion of this one.
If you guys are here, we're going to be here.
I don't
But you might still be on. You might get the end of it. It's my son's class.
Oh, cool.
Yeah. Right. Okay. So we've got that. 6 is.
Okay, so that's secured now, just being pushed down.
That's it. It's not usable. Neither is Fiber 4.2.
Okay.
So it won't be usable now. But interesting to see the sediment properties anyway.
Okay, all done. Thank you.
And that concludes our sampling on this.
Alex, do you expect some lunch from there?
Yeah, you've got it labelled it.
I just sent him a text that. You can gently come up now. I'm just trying to keep this about the same. RV alcohol? Yep.
So these samples will now be brought up to the surface, where all the parts that you don't get to see, where we've got a big lab team together. We'll process these cores, we'll sample them in high detail, we'll describe them in a lot of detail, take measurements and analysis, and this will be for various different types of research. Amongst us, including myself, may be interested in some of these layers. And it might also be that we have eruptions which are recorded as very small shards of glass which have been deposited in these layers. So we sometimes refer to this as cryptotephra, something which is really small. Input. It's not a visible layer to the eye, but at a microscopic level, we might have some tephra in there. We may also have some macroscopic or some visible volcanic ash layers as well. And for the sediment team and for the paleo group, paleontology, micropaleontology group, yeah, I'm sure they'll be packed full of
little organisms as well to work through. So all of our science is really collaborative. It allows us all to work together and to work as a team and share information, which is relevant for relevant for all of our work. So yeah, I'll be pretty busy out on the deck when we pull these up. Everybody getting muddy and dirty, and then into the lab and switching out of overalls and muddy clothes into lab coats and looking more like scientists then.
Check, you got me?
I do. I'll hand it over whenever you're ready.
Copy, probably be about a minute.
No worries.
You let the French know already?
I did.
Oh yeah, I see they're here.
Yeah, that's fine. Yeah. Yeah. So to everybody who's joined us here for the dive or for part of the dive, yeah, thanks so much for your time, and thanks for joining us. Yeah, I mean, when we're out at sea and we're all together, it can yeah, sometimes seem a bit lonely. So it's great that we can share all of this great experience with everybody that's been watching, and share the amazing cool marine life we've been seeing, and yeah, this cutting edge research and science of stuff that's really not been done before. So yeah, thank you very much. I'm sure we'll be doing another ROV dive later today, dependent on factors obviously here, which we'll have to go to do checks and check everything's okay. And yeah, we'll be doing several more dives as well throughout our expedition. So yeah, if you've enjoyed it, please do tune in again, and yeah, come share this amazing art of discovery with us as well. So,
We're gonna all
thanks
stop
everyone.
if you guys take control.
Roger that. Fire in the box now. Roger that. Guys are progressively telling us we're too slow.
No, we're just, keeping you informed.
It's true. Much as it's true.
Yeah. So yeah. So
Okay, I'm ready.
me speaking. Yeah, it's Alistair Hodgetts. I'm from the University of Edinburgh. I'm a volcanologist. So I'm one of the scientists on board the Falcor 2. And yeah, really grateful for everybody who's joined us today, and from the rest of the science team as well. Yeah, it's one of our favourite parts of doing this is being in this control room and sharing all of this with everybody who's watching. So thanks everyone for joining.